Okay, check. One, check.
There you go.
Perfect.
I can just leave it on, right?
Well, you can turn it off if you don't want a hot mic. It's up to you.
It's
And then you should
push
be
it.
good.
Okay.
Yeah.
Good morning, everyone. Happy to introduce our first speaker today of the SCaLE Conference 2025, Sinan. So I'll let him take it away.
Okay, thank you for the introduction. The title is a little bit complicated to read, so I'll just give you like a brief summary of what this talk is about. So I was doing a personal project on a scalable machine learning project on employment data using open source AI. And the reason I was doing this was to analyze the job market trends, classify occupations, and customize job search according to my needs. So in this talk, what I'm going to talk is first start with the standard occupational classification, or it's SOC for short. And I'm going to explain why this is important and why it matters for the labor market. I'm going to be talking about the modeling approaches and some of the challenges I was facing. Then I'm going to continue with some of the other models that I was working on. That includes job title normalization, where I was using embeddings and vector search to standardize some results. Then I was able to do some models for determining the seniority level of the job postings, the employment, like is it full-time, part-time, or is it remote or not remote. There's a personalization aspect, but I wasn't able to wrap it up for this talk, but I'm just basically walk you through like what are the steps here. It's a graph-based recommendation engine for customizing to my individual preferences. And at the end, I will briefly talk about how to monitor all these and how to store these results. So just to mention, like this is a personal project. I work as a data scientist as a corporate job, but this is not related to my corporate job. And I use open source because like there is good active community support. Innovation is like up to date. For me, the most important part was the lower cost, why I wanted to use open source. There are less licensing constraints, and it is also highly customizable for the project needs. So let me start by telling you the definition of what SOC is. It's a framework, and it's used by the US government agencies. And it's used to classify workers or jobs into different categories. And there are 867 different categories as determined by the US government. And these categories are grouped according to the nature of work, the required skills needed for this work, like what sort of education you need, like is it bachelor level, associate level, master's level, and what kind of training goes into for different jobs. And this concept was introduced so that there is consistency across the different departments of the government, such as the Department of Labor or Census Bureau or like Bureau of Labor Statistics. And it's usually used in market trend analysis. It's used for economic research and policy decisions. It's a key tool for program funding. Bureau of Labor Statistics use this to standardize the occupational data. Higher educational institutes such as universities or colleges use this to map their academic programs to SOC codes so that they know the needs of the labor market. And it's also used in visa applications such as H-1B. And why is it important? So it's reliable for the workforce statistics. So if you want to know about the employment rates or if you want to follow different industries and how they grow, it's important to have a good classification. The government actually relies on this data to allocate the funds or shape legislation. And businesses or researchers use these to track emerging job trends, skill gaps, and forecast labor demand. And for me, the personal reason why I was working on this project was I'm an international, I came here as a student, did my PhD, and I work as a worker now. I have H-1B visa. And then I realized that this limits the jobs that I can apply to. And typically the limitation is about the SOC code, as mentioned in the labor condition. So it needs to have appropriate wages and job categories. And the employers must actually follow these requirements so that it meets the correct occupation. So things like the salary are like part of this classification. And if for some reason there was misclassification, like when you are changing jobs, it can lead to audits, requests of further evidence, or visa denials. And it happened to like some people I know, so it was actually very sad to hear about this. But it's also like relevant to wider audience. Even if you are not an immigrant, it still affects job prospects, it affects the salary benchmarks, and possibly the career pathways. Also, companies use this for HR planning, or for like, they want to be like competitive when they are hiring candidates. So here are some, I know it's a little bit small, but I'll try to walk you through. So when I go to different job boards, I see like these 3 different job postings. I didn't really cherry pick them. I tried to show like what kind of problem I'm dealing with here. You can see like certain things, like the description, the length of the descriptions are widely different. The titles are different. So on the left is a dishwasher. On the middle is like travel nurse dash ER slash trauma dash like $2,000 per week. And then there's a location in the job title. And on the right, like you have full-time. So like you have things that are not relevant to job title in the job title. And typically job descriptions are not following a certain format. So it makes it a challenging problem. And this is the reason like why we need to use AI models to be able to tackle this problem. And it's also a complex problem. First of all, I tried to see if there is any open source, if something was already built. I wasn't able to find any good solution on GitHub or in any publicly available repositories. I tried some of the LLMs, including the not open source ones like ChatGPT or Cloud. And some of them perform well enough, but the information there could be outdated. And it also becomes very costly when we try to scale this up. The open source models were not also capable of producing good quality results. So, so what's the complexity? So there are, first of all, like a lot of different categories, so 867 of them. And just to define a classification task with this many categories is actually challenging. But also the job descriptions, they are not always very structured. There's varying language. There could be like plain text, marketing language, or technical jargon. And the formatting is also inconsistent. So some of these job postings, you can find qualifications, responsibilities. In other ones, you might not be able to find them. And yeah, there's basically like no consistent format to the job postings. And there's also a significant overlap between different categories, which also makes the problem very complex. So let me explain like what I mean by some of these. So here, this is from the ONET. It's a publicly available page by the government that lists all these different categorizations. So these are 2 different categories. They are both in wholesale and manufacturing. They are both sales representatives. And on the left is excluding technical and scientific products. And on the right is including, or just capturing that part, like the technical and scientific products. So you could see like why this is a difficult problem, because even for humans, it would be challenging to determine which category the job could fall into. And then there are also roles that could fit into multiple SOC codes. An example could be a data scientist and an analyst, because typically the job descriptions could be very overlapping. Like you are using a lot of like statistical work or engineering tasks for these kinds of, both of these jobs. And it's easy to like get confused between the different categories when there is a lack of clear distinction between the categories. And as you will see later in the talk, like the classification algorithms also get confused. especially when we try to do it with job titles or keywords, it's not able to capture all the niche components of the jobs. So we need sophisticated AI models to capture these. The way these codes are structured are they follow a hierarchical approach. So there is the 2-digit codes, so they represent major groups, and they have a broad occupation family. An example would be computer and mathematical occupations, and we can dig deeper. So if we go to 4-digit, it's a subcategory within the major group, and this would correspond to like software and web developers, programmers, and testers. But if I want to really go into the specifics, then I would go to 6-digit, which is software developers. And trying to build models with this approach failed, because first of all, there could be 2 different SOC categories that belong to different 2-digit codes. As you can see here, on the left is the exercise trainers, and on the right is athletic trainers. And they look fairly similar for a model. And like you can have similar keywords like trainers, fitness, but still like the model will not be, or have a hard time distinguishing these two. But also if you try to start with the 2-digit approach, like the errors on the model add up, which means that, okay, let me first find the 2-digit, but the moment you make a mistake, you also make mistakes in the subsequent routes. So this wasn't a good path to follow. So yeah, I had to build a training, test, and validation set. And for that, I had to collect a wide range of real-world job descriptions. And I had to actually manually label them. So I was using Label Studio, which is a state-of-the-art open source labeling program. And I was using Llama for making the annotation a bit faster by pre-labeling some of the jobs. And in some cases, there weren't enough jobs to represent, so I was asking Llama to regenerate job postings for me. And I set at least 10 samples per category for a minimum baseline to fine-tune a model. But typically, like, you would need more data for a better performance. So the coverage was about 10,000 labeled job postings. And I did a splitting of training, test, validation, 80%, 10%, 10%. But the important point here is each of these SOC categories get this split differently, so that we have enough testing and validation representations from each category. And I'm also aware that some jobs could be very niche, and they might not be represented well in the training data set. It's a very resource-intensive task to do, but it's very important for accuracy. And we need to have like a good, well-balanced validation set so that we know like what the strengths and the weaknesses are. And the reason why we have test and validation differences, tests tell us when to stop our training, and validation tells us, okay, like you are done with training, let's do an independent check how well the model performs. And when I report the results, I report the 6-digit, 4-digit, and the 2-digit classification accuracies. So first, I want to set a baseline by like rule-based methods. So I use fuzzy matching. So there are SOC titles available from ONET, and I compare the job titles from the job posting with the SOC titles. And these include word and character level similarities that are applied to titles. And it would give me the baseline. So any subsequent AI model I will build, I would want it to actually beat these results. And the results were actually close to 40% for the 6-digit, so there's a typo here. For the 4-digit, it was 51, and for the 2-digit, it's 66%. And the main reason why this failed is because most of the time, like, the job titles could have noise in it. So like things like training provided, or in some of these more modern job postings, you can see terms like rockstar. There are also things like $50 per hour, remote. And this also led me to develop another model called the job title normalization model, which I will also walk over. But this tells me that I need to move away from rule-based and fuzzy approaches and go to more sophisticated NLP techniques. And currently, like one of the state-of-the-art models is transformer-based models. And in this case, like I'm only considering encoder-based models, which means that I input words or sentences, and it gives me like a classification layer. Some of these models include like BERT, Roberta, and DeBerta. The way transformers work in a nutshell is they have a self-attention layer, and it can capture the relationship across every word. So it doesn't look at sequentially, but it looks at like word by word products and see like how they are relevant to each other. And this helps the model understand the context really well. So I was testing with like Roberta and DeBerta, and the fine-tuned weights, or so the trained weights are available on Hugging Face. They are typically built on top of PyTorch, and there are pipelines available to fine-tune according to my specific needs. And I was expecting the models to perform really well, but they actually performed much worse than I was expecting. So the fuzzy matching was giving me close to 40% accuracy on the 6 digits. And if I were to just randomly guess, I would expect maybe around 0.11% on the 6 digits. And when I was looking at these models, they were giving me like some of them slightly better and some of them even worse than random results, including a case when it's like 0% accuracy for 6 digits. So clearly something was wrong here. And I spent a lot of time like debugging the code because I was sure there's something wrong with the code. But when I use publicly available data sets for the same pipeline, it was giving me good results. So I started to dig deeper, like why are these models performing so bad? And the most important reasons is because different categories have overlapping, a lot of things that are overlapping, including like skill sets and responsibilities. So as mentioned before, like when we have data analysts and data scientists, they might share 80% of their tasks. But what we are doing here is we are instructing the transformer to pick one over the other one. And it gets confused. So when we say a job is data scientist, we are saying this job is definitely not a data analyst job, and vice versa. But there is like a lot of overlap. And it was preventing the model from learning what we were trying to do. So what I found out here is that transformers need very clear, distinct signals to differentiate the different classes. And they struggle when the job postings are vague or closely related. So even though the attention mechanism is good at capturing the context, like it still needs clear distinction in the text. And even though these are like some of the state-of-the-art models, like the accuracy was just very bad. And we had to come up with another approach. So it's called contrastive learning. And just to give you a brief approach on a brief introduction to what this is. In contrastive learning, we are looking at pairwise. Like we look at each label pairwise. And we are trying to bring pairs that are similar to each other, close to each other. And if the pairs are different from each other, like we try to split them away. And this is especially powerful when there are like more subtle distinctions between the classes. And it's giving you like pay more attention to the nuanced features, like in the case with the analyst of the data scientist. And I think the figure will be able to make it more clear here. So if I were to do this kind of approach for pictures, let's say like cats and dogs, I mean, the first approach I tried to do is like, these are all cats, so I put them in a cat category, and these are all dogs, and put them in a dog category. But the different way to approach here is like, you say the first picture and the second picture on the left, they are the same. But then you say like all these cats are pairwise the same. So it's here, like on the bottom side, it tries to bring the cats together. And you do the same thing for the dogs. So like it tries to bring the dogs together. And if that was all you did, then okay, it understands that you are supposed to bring the cats together and the dogs together, but it doesn't understand that they are two different categories. What you have to do is for each similar pair you identify, you need to also mention that there could be different categories, and you need to specify that you need to actually provide a distinction between the cat and the dog categories so that you can get this nice boundary between the different classes. So I start to apply this methodology to the training set I had. So the positive pairs would be correctly labeling the SOC labels, which I use for the transformer model. But then I have to do like negative pairs. So for each positive pair that I identified, I had to identify 40 negative pairs. A good way to deal with this is, like an easy way, let's say, is matching the negative pairs from different two-digit categories so that they are distinct enough. But if you have like more resources, then like if you have an annotation team or have more resources to work on this, it would be even stronger to do like data scientist, analyst kind of distinctions. So now the model learns to cluster similar occupations and tries to push away the dissimilar ones. And it gives you actually a ranking. So it will say that, let's say if this was a data science job, it will hopefully bring data scientists as the first, like the top ranking. And then it will probably bring data analysts in like the top 5, top 10. So now the model doesn't get confused because now we are not instructing model to say like, if this is a data science job, then it's not a data analyst. So there is no confusion with this. And the best model after like trying out a lot of combinations, the 6-digit results were close to 61%, and the 2 digits were close to 85%. And if I look at the ranking, the 6-digit matching is in the top 3, like 74% of the time. This could easily be run in commercially available GPUs. So I tried this on a 4090, and I could actually process about 100 to 200 jobs per second in batch mode. And I wanted to do a comparison with like how does GPT-4, which is like one of the state-of-the-art LLMs, perform on this task. So on the validations that I was looking at, the 6-digit was about 63%, and the 2-digit was 84%. So the results are actually quite comparable with each other. But if I were to do this analysis with GPT-4, the estimated cost would be around $2,500 for 1 million job postings. And just to give you a scale, like typically there are a few million job postings per month at job boards. So, and I was thinking like, what else can I do to improve some of the, like the quality of this whole process? One thing is title normalization. So I collected publicly available data sets to create a taxonomy. And the goal is to standardize or maybe like normalize job titles. So when you go to a job board, like you see afternoon assistant teacher, parentheses 3 p.m., 6 p.m., like it would remove the part that says 3 p.m., 6 p.m. and put it into predefined categories. So if you have a good taxonomy, it should be able to handle most or all of the cases we have. And the approach was actually begin with this list and use some open source embeddings to represent job titles as vectors. And I was using Face. It's an open source vector search provided by Facebook. It lets you find the closest normalized titles by measuring the similarity in the embedding space. And this actually helps improve the consistency in the job title data and helps us improve our SOC model as well. And why are we using Face in this case? why don't we use just like a full KNN approach? Because the number of job titles are very high here. Like we have 20 million unique job titles, let's say, and we need to choose from like 50,000 normalized job titles. Comparing them becomes very computationally very expensive at large scales. And instead, we introduce a small tolerance for approximation to find the top case similar results. And the way this pipeline works is convert titles into embeddings, build an index for the vector search, do the similarity search, and return the results. So yeah, like one of the use cases is the title normalization. And the other cases, we can use exactly this methodology to detect almost duplicate job postings. I'm not going to go into too much detail here, but if you were to go through that route, most of the time, like recruiters or companies, they put a lot of job postings online, and they can sometimes put exactly the same job postings, and other times they can change a few words here and there. Yeah, like if we were to try to do a hashing-based approach, we wouldn't be able to find the exact, also almost exact duplicates. So we would need to use this kind of methodology to detect these duplicates. And what's the trade-off for using approximate nearest neighbors? So there are a lot of publicly available benchmarks. But what you are seeing here on the x-axis is the recall, like how accurate our models are. And on the y-axis is how fast they are at retrieving answers. And as expected, the less accuracy you have, the faster it is. So you need to decide what's the tolerance level you want and what's the latencies you're expecting. Yeah, so we can also do additional modeling here. And this is to use more keywords, such as like a TF-IDF approach, where we look at the term frequencies. And it measures how often a word appears in our corpus. But we also want to make sure we are filtering out words that appear in every job posting. So like we would look at inverse document frequencies, like words like and, they would appear in every posting, so they would get downweighted. So we can use this to find additional features, such as like what's the seniority level expected for this job. And when I used this approach, these were some of the important keywords that came up. And you can see that they are highly relevant, like director, intern, leadership, manager, like experience. And if we couple this with the Roberta approach, we just pick a few sentences around these words for each job posting, we can actually achieve about 84% accuracy on our validation data. So I'm not going to go too much into detail here, but the next thing was to build a personalization aspect for my own needs. And a good way to represent the data is using graphs, using like a Neo4j, the community edition. And each node can represent job postings, companies, locations, and skills. And edges would represent like required skill, located in, reports to, so on and so forth. And also a graph would be really good to handle duplicate job postings, because then we can represent duplicates as traversals in a graph. But this is, yeah, still in progress. The results are served with Fast API and Gradio. So it's very lightweight and easy to build RESTful APIs, and it allows asynchronous calls. So there's also the interactive front end with Gradio. All of these are containerized and packaged in a container so that the environments are consistent across different deployments. So this is what like maybe a snapshot of the code looks like, and these are the different endpoints that I was working on for this project. And I can actually serve the results with an interface. So I can put the job title here, the job description here. I can choose which model to run, and it will bring me the SOC code and how much time is needed for this model to run. And I was monitoring this process with Grafana. to track like what's the CPU, GPU, memory usage. It's open source, and it lets me like handle also like multiple machines at the same time, like it's highly scalable. And this is some of the monitoring aspects I was doing while I was fine-tuning, and I was checking the, when I deploy the models and I want to do like testing how much resources I'm using, I was checking through here. So just to recap, like the open source tools I was using, like within the Python ecosystem, I was using PyTorch and Hugging Face transformers. And I was using Face to do the vector search. I curated data with Label Studio. I served the data with Fast API, connect to Gradio, and put everything in a Docker container. Later used Neo4j with Grafana for the graphs and monitoring. And some additional tools are the TF-IDF from scikit-learn and some other ML utilities. So to give a conclusion, so the main takeaways are the SOC classification is vital for understanding the labor trends. And there are open source tools available that could help us classify the SOCs with minimal cost. And even though it was like a very nuanced NLP approach, like we were able to solve these issues. And looking ahead, like I want to finish up the personalized recommendation and the graph-based solution to unify all these aspects. And I want to contribute back to the open source community with the lessons I learned, with the codes I've written, and like with the best practices throughout this process. And open source was able to provide like powerful tools to solve these real world challenges. Like with community collaboration and with iterative development, like these can have actually significant impact on research and industry. Yeah, this concludes my talk. Thank you so much.
Thank you very much for that presentation. We're going to take the next 10 minutes for any questions on the floor.
Thanks so much for the talk. Really appreciate you putting together all that data, especially to show, it helps to not just hear about what you've built, but also see the charts and comparisons. Mm-hmm. If I'm understanding correctly, would you say that the biggest, so like when you're comparing GPT-4o versus, the system you built, yeah, thanks. Would you say that the accuracy was pretty similar? Are there any other aspects that aren't listed here, in these 3 accuracy metrics where one performed better than the other? Is the biggest differentiator like the cost and the time to develop?
Mm-hmm. Yeah, and also the latency is a big factor here. Like if you want to build a large-scale application, like let's say you want to actually classify all the jobs to SOC, apart from the cost, also the time it would take GPT to do this would be significantly longer too.
Thanks. I had a kind of follow-up question about that too. How did you implement the classification in GPT?
Basically just preparing prompt, like, hey, this is the job description, and classify the SOC. So I didn't provide the most recent SOC list. I'm just taking, I'm just assuming ChatGPT knows the different SOC categories, which could also be outdated. I think a better approach to use GPT-4 here could be to build a RAG system that you can actually put all these different categories and build like a pre-processing step and say like, these are like maybe the 20 candidates I found. Given these 20 candidates, like what is the best matching case? I think that would improve the GPT-4 accuracy. Yeah.
Thanks.
I want to say excellent presentation. I loved how you walked through all the different steps on it. And you actually just kind of summarized the comment that I was going to make of having a mixed model approach, where you bring in first the kind of the best model to filter out I would say the top K, whatever that is. When I've done similar things before, it can be 5 or 10, and then passing it to GPT for that kind of like longer tail, higher parameter classification. But I love the work, and thank you for sharing this out. Great project.
Oh, thank you.
Just thank you very much as well. I really appreciate this this talk. Two questions for you. One, did you, since you have labeled data, did you fine tune your GPT models at all, or did you
I
just use
didn't
raw?
do that, but I think it would be a good approach to do as well to also
I mean,
compare that.
I've seen significant performance improvements when you do a fine tuning with labeled data, so you might be hamstringing it here a bit. The other question I had was, you're doing positive and negative pairs. Did you consider doing contrastive triples?
I didn't know.
Okay.
Thanks for the talk. Can you talk a little bit more about the part about like creating the taxonomy and doing the data annotation? Because I'm wondering, like, did you have someone volunteering doing that? Were you using something that was already, you found like something like open source, like a taxonomy? Because that seems like kind of a heavy lift.
Yeah, some of these were like open source available through ONET, which is a government agency, but others were not as open source. Like I had to dig through and come up with also like my own taxonomy to represent as much as possible. I think there could be more work done here, since like if we have the job titles, we can also build models to determine what are the, like do some clustering analysis there to come up with a new taxonomy, so we don't have to depend on external taxonomies. But yeah, that was beyond the scope of this project.
Thank you. That was a truly excellent presentation. I noticed that used Python stuff. That's an obvious choice. Have you had any luck looking for other languages? Some people prefer non-Python stuff for AI, and they're sort of out in the wilderness. What's your opinion about the opportunities for using other languages for driving AI?
So that was just my personal preference, because I'm more familiar with Python in AI context. I think if you want better latencies, I think C++ could be an option for some of these components. One of the things I was considering is actually using C++ to model the graph part. Let me go to the, yeah, this part could benefit from maybe some C++ relevant work to speed up the graph algorithms if we don't go like through the Neo4j route. But otherwise, it was mostly like a personal preference why I used Python.
Anyone have any more questions? All right, give it up again for Sanang.
Thank you.
Thank you for that presentation, and thank you all for attending.
Check, 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 check. Eeny, meeny, jelly beanie. The spirits are about to speak. Testing, testing, 1, 2. Show of hands, can you hear me? Okay, it needs to be a little louder. How to volume control? Let's help. Well, maybe I'll just move it closer to my mouth. Hopefully I won't have too many pops and hisses.
No, I don't think so, but yeah.
All right. Can you hear me now? All right. Okay, let's see. How much time do we have left? 3 minutes. Tick-tock, tick-tock. Yeah, you can tell I really hate coming out and interacting with people. It just sucks. You guys are all so weird, you know. No, seriously, one of the things I was thinking about as I was walking around, I'm seeing all of the very different presentations that people have, and I love it. The different colors of hair, the different styles of dress. We've got large, medium, small, oh my God. You know, it's wonderful to see this variety of humanity in a group all coming together with similar interests and wanting to share information with each other and connect in a positive manner. It really is very reassuring in these troubled times. No? It's up to you. Your discretion or the lack thereof. I just work here, man.
Afternoon, everyone. I have the pleasure of introducing Ms. Acker and her presentation. After she's done speaking, we will reserve some time for questions. So I'll let her have the floor.
Well, thank you very much for coming to my talk. This is a subject, well, my latest obsession has become AI and LLMs, and as someone who works professionally in cybersecurity, there's there is a lot there too, and because AI in the mainstream is so relatively new, I have a very keen interest in doing what I can to help make sure that as this technology evolves and moves forward, that we do so in a manner that is empowering for humanity and will not be used in a negative way. So, to that end, the talk is Keeping Things Local, How to Make Your Own Private LLM. Things that we are going to explore. We're going to do a brief overview of what AI and LLMs are and talk about why you should keep an LLM local. You may or may not have needs for this, but I know that intelligent, aware people understand that there are both security and ethical concerns about the abuses and uses and abuses of large language models, especially in these days. I'm going to discuss some popular local LLM options. Unfortunately, I will only have the opportunity to demo one, but you folks, you're Linux geeks. So I went with the command line option. You can explore the GUIs on your own time, okay? I'm also going to show you how to enhance your LLMs, because that's when it gets really fun. The speaker who was in this room before got into the data science and working on doing a lot of analysis. Wonderful talk, really good content. But I'm going to be hitting things at a little bit higher level. And so in addition to the demo of how to install and run Ollama, I'm also going to demonstrate how to take an existing model downloaded from Ollama or Hugging Face and how to customize it to help meet your more immediate needs. Now, why should you give a hoot what I have to say? Well, let me tell you. Hi, I'm Bronwyn. In some circles, I'm known as Corvus. In others, I'm known as the Cybrarian. So take your pick. I've reached that age where it's embarrassing to talk about how long I've been doing stuff. So I have over 30 years of development experience. That includes web, desktop, mobile, and a partridge in a pear tree. Anyway, I also did technical training for over 20 years. That was my primary source of income for a long time. So part of the happy-go-lucky, easy banter is because this is definitely not my first rodeo, and it is such a joy to be able to share information that I have with you and hope that you will take it and do great things as you go forward in your own lives. Back in 2017, I decided that the development world was not doing it for me anymore because I'd been there, done that, so I switched over to something nice and easy like cybersecurity. Yeah, right. In 2018, late 2018, a guy named John Strand at Black Hills Information Security said, hey, you want to come work for me? And so I've been doing everything from editing penetration test reports. I think I did some number crunching, and at this point I think I've read, edited, or co-authored somewhere between 1,200 and 1,500 penetration test reports. So yeah, not a couple. And these days I'm doing other stuff, but my main obsession these days is AI research. And as I said, I want to make sure that we don't wind up having to deal with the T 1,000, 2,000, 3,000, whatever. Bottom line, I'm a geek. I've been around for a while, and I've seen a lot of natural fertilizer. Full disclosure. Got to have full disclosure. This presentation was created using AIs like ChatGPT, Copilot, DALL-E, and Midjourney. However, they were at all times under adult supervision. Now, you'll notice the asterisk. The caveat is that you must assume that I am an adult in order for that to really work. So let's get down to brass tacks. What is AI? AI has actually been around for decades. AI has actually been around for decades. It is the field of computer science which is aimed at creating systems to perform tasks that would normally require human intelligence. So this is a key thing. AI, the large field that is AI, is all about simulating and emulating human intelligence. We're not there yet. We are getting closer, but we're not there yet. So AI includes things like robotics, like computer vision. That's what lets computers do things like OCR, face recognition, and other things that sometimes are fun and sometimes aren't. Natural language processing. That's the aspect of AI that helped lead to things like LLMs. And then we've got expert systems where we're able to train a system to do one specific thing very well. An example of that is some of the things going on in the medical field to identify cancers from x-rays. Those are expert systems with a very specific function and lots of cool things going in. So LLMs fit within this larger ecosystem. They are a subset of generative AI. Now, generative AI is a little bit different from what you would use for robotics because generative AI or Gen AI is where the AI in question is generating something new using the ingredients, the data that it has already been fed. So if you're dealing with something like Midjourney, it only generates imagery because that's what its field of expertise is. Then you have LLMs, which are text-based, And so they are dealing with words and language. You will also have AIs like ChatGPT and others that are multimodal. They do more than one thing. So, just be aware of that. LLMs are probabilistic. Yeah, that's got a lot of syllables there. Probabilistic means it's based on probabilities. So you know how when you go to a website and you start typing things in and it starts auto-filling because it's anticipating what it thinks you are going to say next? That's the same kind of thing. So LLMs are probabilistic. They're taking what you put in the form of a prompt, and they're going to take it and then using the probabilities figure out, oh, this word is part of the prompt, then this is the trail that I should follow, and it gets very complicated, and the data science genuinely will melt your brain, blow your buffers, but if you're sick like me, you will enjoy most of it. Current models are trained on massive amount of data. This is both good and bad. It's good because they have a lot of raw ingredient to pull from. It's bad because there's lots of garbage in there too. One of the things that has been coming out a little bit more is that the large language models like ChatGPT and others, they have Russian disinformation BS in them, in addition to other legitimate good content. Well, what did you expect? You trained them using data that you scraped off of the entire internet. So, no surprise there. Most of your LLMs are going to be general purpose. You can ask them about Linux commands, you can ask them about Python code, or you can ask them for how to make a better creamy rice pudding. It's going to do all of it. But there are some that are going to be specialized, and I'm going to talk a little bit more about that as we get deeper into the weeds. And again, AI has been around for a long time, but with the development of the large language models and ChatGPT in particular, easy access to LLMs has popularized AI as never before. Excuse me. So, why go local? That's why you all are here, right? Number one reason is privacy and security. No data will leave your machine, network, or intranet if you are running a local LLM. And local LLMs are not just for individuals. They're also for organizations. So something for you who are in IT and help desk, you may want to consider training or customizing models for your specific use cases to help make you more efficient, or at the very least, help people find the any key more readily. The other thing is sensitive files and data remains within your control. I do not care what the EULA says. If I am sending my personal information, forms, documents, whatever, that have sensitive information, if I'm using a third-party chatbot, first I have to send it out over the internet, it has to interact with their servers, and it has to be sent back, and at some point, the third-party service could get popped. They could get breached, and whether or not they're training based on my data, they're going to retain it for some period of time that I have no control over because it's a black box. So keeping that sensitive data and those files in your control is a really good justification for going local. The other one is customization. You can fine-tune it to your needs. Those needs can be frivolous or serious. You can create custom models. You can use retrieval augmented generation. I hate that term. Can we obfuscate more, please? Retrieval augmented generation means that you have a stack of data or documents, and you have them here, and then you have your LLM, and then you have your user. Your user interacts with the LLM, and the LLM interacts with the data and documents. So in essence, the user is able to interrogate the data and documents in a meaningful way, hopefully to get usable information and knowledge in a much more rapid manner. Finally, if you want to go deep down the rabbit hole, you can train your own models. I recommend that before you go down that rabbit hole, you get some data science chops under your belt, because that's what you're going to need to do it well. So, I work in cybersecurity. My bachelor's, my master's are both in cybersecurity, so I'm going to talk about cybersecurity. Whoops. What did I do wrong? Go back. There we go. Jailbreaking and prompt injection is where hackers go first. Every single LLM is susceptible to jailbreaking and prompt injection. What that means is a hacker will go to whatever the LLM or other AI is, and they will convince, coerce, harangue, or just flat out attack said AI and get it to do stuff it shouldn't oughta. And those shouldn't oughtas include data leakage and privacy breakdowns. So come on in. People are nice. They won't bite. They might if you ask nicely. Another concern is model bias and poisoning. Now, I am about to make a statement that some people might consider a little hysterical, but bear with me, and I think you'll understand when I get to the end of this little spiel. Every single LLM model out there is biased, and there is a non-zero probability that if you are anything other than a white cis male, that bias is not in your favor. Okay? Now, there are very good reasons for this. Remember what I said before about LLMs being trained by data scraped off the internet. Okay? Now, model bias is different from model poisoning. We're seeing in cybersecurity a significant uptick in model poisoning, and that's where malicious code has been injected into models, and then they're uploaded to GitHub or Hugging Face or some other repo. But model bias can be, it's the same kind of insidious thing that prejudices can be. Now, can we eliminate bias from LLMs? I don't think so, not completely. And the reason is simple. As human animals, we are intrinsically biased. So, for example, I am 60 years old, white, female, 5'2", and I'm not particularly religious. I'm more of a humanist. So I have biases that are based on my personal experience. I have a very dear friend that I've known for 30 years. He is similar in age, also white, but he's male. He is also several inches above 6 feet, and he is religious. So we have some commonality, but he's going to have biases that are different from mine. And it may be that you will want to create an AI or an LLM that increases biases in order to better serve the purposes that you are trying to achieve. So for example, if I'm doing work for a nonprofit that is serving homeless people who are in a predominantly black region, I'm going to want to create LLMs or other AI that are biased in favor of those populations so that that nonprofit can do their job better. Conversely, if I'm working for an HR department or company, excuse me, I'm going to want to minimize the bias so that people who have black-sounding names are not discriminated against in the hiring and interviewing process. So there's a time and a place, but as technologists, we would be irresponsible not to acknowledge and address and deal with biases in these AI. All right. Climbing down off my soapbox. Another thing that we're running into is social engineering automation. Phishing emails have gotten harder to detect because the bad guys are using AI and LLMs to crank out better phish than ever before. Also, we've got the usual suspects. Poor API implementation and authentication controls are going to shoot you in tender portions of your anatomy every single time. And there are people here from OWASP. Talk to them if you don't know what I'm talking about. All right, components to build a local LLM. This is where we get into the meat of what we all hear about. The first thing you're going to need is hardware. And GPUs are very, very useful. But truthfully, they're not 100% necessary. It just means that when you run the LLM, it's going to be slow, it's going to be sluggish, especially if you're using a large model. So GPUs are really, really nice to have. They absolutely will improve performance, but they get expensive fast. The other thing you're going to need is RAM and disk space. Now, here I've said 16 gigabytes or more. I want to emphasize the or more, but you guys, you know and I know RAM does not stand for random access memory. It stands for rarely adequate memory. So, and I say this as a woman, I've got 96 gigabytes of DDR sitting on my desk that I haven't plugged into my system yet, but you know, that's the kind of thing that I have so that I can do more, especially as an AI researcher. The other thing is disk space. 50 gigs or more. Again, more is better because, especially because some of these models, what the latest Llama 3 is 70 gigabytes. No, it's 70 billion parameters, 40 gigabytes, and that's just one LLM model. Again, bigger generally is better, maybe not 100%, but you will run out of disk space fast if you are downloading a lot of stuff. The other thing you're going to need is software. Your software choices will determine your UI, your user interface, model management, and other capabilities. Now, again, I mentioned I'm only going to demo Ollama because it is CLI, but LM Studio is a very nice GUI, has a lot of positive things about it, and it has native RAG functionality built into it. GPT for All, I'm hearing about more and more. I have not had the opportunity to really play with it on my own, but again, what I've been seeing and reading from other sources that I consider reputable, it's getting some good feedback. Then you have your LLM model itself. So again, you've got the hardware, you've got the software, the model is what has the data. By the way, I will be posting this entire slide deck to LinkedIn as a PDF. So I understand you're taking pictures, but also know that it'll be available on LinkedIn for people who want to look it up later. So open source models are available from Hugging Face, Mistral, Llama, others. Llama 3, DeepSeek, Phi 1, Mistral, Gemma 2, those are some examples. You may or may not have heard those names. If you are going to be getting into this, you will hear them. You will hear them more than once. Talked about GPUs, let's dive a little deeper. NVIDIA they have the corner on the market. They effectively have the monopoly. There are other ones around, but they are the best game in town. I'm just going to throw these different models up, and I'm not going to go through everything, but my system, I've got the RTX 4090, and I kid you not, being able to do the demos, prep the demo recordings that I'm going to show in a little bit, it flew much, much faster than my old system was able to handle. If you are living the lifestyle of the rich and shameless and money is no object, then you're going to be going for the H100 and probably have multiple in an air-conditioned server room or something. I don't live like that, but there are options that are available that won't completely break your budget, and again, it depends on how deep you're going to go and how intense it's going to be. Now, AMD does have limited AI support. The Radeon RX 7900 XTX, blah, blah, blah. It has a lot of VRAM, but it's using ROCm, which is the Radeon Open Compute, which is their open source GPU computing platform. NVIDIA uses CUDA, C-U-D-A, which is Compute Unified Device Architecture. Yes, it's proprietary. Of course it is. So, Ollama software, let's talk a little bit about that. Command line interface, open source, MIT license, usable on Linux, Mac, Windows, Docker. Lots of options. There are active communities on Discord and on Reddit. So please, absolutely go to those and, use ChatGPT, Copilot, Claude, Perplexity to help you answer questions when you run into stumbling blocks, because anytime you learn something new, you will. When you are using Ollama, the polls of the models are coming from Ollama.com. LM Studio, which I have used and played around with, and I do really like some of its features, it has both GUI and CLI. So if you're one of those people who's always running your Linux headless, you can do that with LM Studio too. It is developed and maintained by Element Labs Incorporated, so no, it is not open source, but it does have a limited license for personal non-commercial use. It is usable on Linux, Mac, and Windows. Their community is mainly Discord-based. And instead of pulling from their own repo, they are pulling from Hugging Face. Going to talk more about Hugging Face in a moment. And I think I mentioned before, it has native RAG features, which is really sweet. Lots of other options available. This is, it's really a field that is exploding. No, I have not used all of these other things. And truthfully, if you explore these other tools and you have positive or negative experiences, please, please, please let me know, because I can't do all of this. I'm only one human, and I would love to be able to speak. If I don't know about something, I don't have an opinion. I can't have an informed opinion without having information. All right. LLM model repos. Hugging Face is the largest repository of open source and various licenses for LLM models. Ollama.com, simple one-line command, let you pull a new model. It's really sweet, as you will see. Mistral, Meta, Google, lots and lots of options. When you choose an LLM model, they are not all the same. you know what, I'm going to skip through this because really what you want to keep track of is the model size. And when it comes to LLM models, it's not just disk, how much the file takes on the disk. It's the number of transforms. So I'm going to deviate from what I had planned to say a little bit. The way that generative AIs are created, and if you haven't attended any of the other AI discussions, this will probably be new information. Basically, they take a lot of data and then they chunk it down into small nuggets that are called tokens. And then the tokens are the system is trained so that this token connects to this token, connects to this token, and that's where you get the probabilities. And so when you see it's got 70 billion transforms, that's because those transforms are the jumps between all of the different tokens. And the aggregate of tokens contained within that single model will be 1, 2, 5, 90 billion transforms. So it makes a lot of difference. Now, the problem is more parameters. Yes, it means more data, better accuracy in general, but it also means that your computational needs are higher. So I tried to download and run the latest version of Llama 3, Llama 3.4, I think, on my system. And again, using a reasonable GPU with 24 gigs of VRAM and 36 gigs of regular RAM, and when I tried to run it, it went pfft. And that's only 70 billion transforms. So no, I didn't bother recording that demo because why? I can tell you about my failures, I'm not going to showcase them. And then you've got models that are general and specialized. There are specific models available for math and for coding in different languages. So lots and lots of stuff to choose from. This is what the Ollama website looks like. This is what it looks like coming straight in. And you can go into that field and just typing the word code, you're getting a much different response. Ditto Python. Ollama has thousands, but, oh, and when you drill down into it, it's going to give you a lot of information, how many different versions of that model there are. So in this case, Llama 3 has both 8 billion and 70 billion that are available to download, and there's metadata, and there's also the one-line code to be able to pull it and run it. When you go to Hugging Face, it's a little bit different. Hugging Face has many, 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 many different kinds of models. So not just LLM, but also image-based, image to text, text to image, voice, and so on and so forth. As of earlier this week, they had nearly 1.5 million different models available for download. These are only the public-facing ones. Once you set up a Hugging Face account, if you want to train and store models on their host, you can do that, but you can flag them as private in a similar way that you can flag things as private on GitHub. Now, by refining the search to only models that deal with Python, I dropped the returns down to 1,735. So again, it's about asking the right question. And now it's demo time. And I forgot to set my timer. How am I doing for time? Oh, okay, that's a problem because I have 18 minutes of demo. All right, so Ollama.com, we start here. And come on, go away. I want that bar to go away. There. And you have GitHub. You're going to want to go to the GitHub and scroll down through the README. Again, Mac, Windows, Linux. Yay! One-line curl command will pull and install Ollama on your Linux system, whether it's Linux on bare metal or WSL or something in between. Now, I've set this up where I have 2 shells running. There's a madness to my method, bear with. So I've pasted the command, and of course I have to have my password because it needs to get super user whatnot, and we're off to the races. Now, this is another reason why I record my demos, aside from the fact that the demo gods are mean, vicious, and cruel. You don't have to wait through the entire download. And the install is complete. And run just Ollama. Yes, it's successfully installed, so it wasn't lying to me. Trust but verify, right? And let's zoom in a little bit more, hopefully. Can you read this okay? Yay, all right. Now, I tried to list the models that I had, and it said, what? Well, that's why I have the second shell, is because I need to be running Ollama as a service in order to be able to interact with it. So Ollama serve is the command, and yay, we're off to the races. At the bottom of this wall of text, you can see that it has recognized the GPU and its capabilities. Now, even though I have 24 gigabytes of virtual RAM, it's only going to take 16. And this is a common characteristic when working with LLMs and AI in general. So, all right, but Ollama list, it worked this time, and it shows that I don't have any models installed as yet. So now I'm going to go to Ollama, and I'm going to surf around and look for different models. By default, they're sorted by popularity. You can sort them by how new they are. And I showed you the ability to search for things. I know DeepSeek is in the news a lot right now. I'm not working much with it because I have trust issues. And I'm not afraid to admit it. So I'm going to start off with one of the Phi's. Phi is comparatively lightweight, but very, very responsive. And Phi 4 is still 14 billion parameters. Yes, it is made by Mickeysoft, but I don't hold that against them. You can see the metadata, but of course, the most important part of all of this is that wonderful one-line command, Ollama run, and then the name of the model. So, copy it to clipboard, go back to my shell, paste. And what I did for this first run was, instead of just running this command straight, I'm going to edit it so that instead of pulling and running the model, I want to just pull it. And with the miracle of video editing, we will speed through the download process. Like I said, demo gods are mean, vicious, and cruel, so if they're going to fight dirty, so will I. So once the model itself downloads, additional files will also download. Your Linux people, you understand dependencies. Writing manifest, it checked the SHA, it wrote the manifest, success. Now let's double check that, yay! And 9.1 gigabytes on the disk. So now I'm going to actually run it. So the syntax, Ollama, what you want it to do, the action, and then the name of the model, and hello. Let's see. Oh, yes. I need a recipe for creamy rice pudding. Can you help me? I don't know. When I was doing this, I was jonesing for rice pudding. It was late at night. I was tired. I wanted carbs. And there you have it. Not too bad. And all on the local disk. All on the local disk. I didn't have to run it over an API. If I had pulled the model and then isolated it, cut all network access, I still would be able to do this. So let's pull another model. But first, let's clear up, tidy things up a bit. And this time I am going to pull one of the llamas. Again, llama 3.3, 70 billion. Yeah, not happening, not yet. Llama 3.2 has two options, 1 billion and 3 billion. The 3 billion is the default. So let's pull that. Go back, paste. That is one thing that I do like about working with WSL. It is easier to paste than it is on straight Linux. One less key, I know. All right, and downloaded. And because I did run checks to see if I have the named model on the local system. If it is present, then it will immediately launch. If it isn't present, it will do a pull from llama.com. And it went straight in. So I'm going to ask this different model the exact same question. I'm jonesing for rice pudding. Can you help me out? So the output here is a little bit different, and it is not uncommon. You folks have used LLMs of some point, so you may or may not have noticed that sometimes if you ask the exact same question more than once, you will get different answers. Less common if you're using Copilot. Copilot is just a skinned version of ChatGPT, but with more guardrails.
The question is, can it handle the load, and based on the amount of data and the type of, how do you get it out of the database as well? So there are many different vendors out there right now are able to store vector data. Cassandra is one of them. They are purpose-built databases like Pinecone, Milvus, Weaviate that are meant for this type of data. Other databases have add-ons. Postgres has pgvector, which then you can, if you're already using Postgres and you want to have some vector data, you can have it in Postgres and still use it. But the advantages of Cassandra compared to the rest is that with Cassandra 5, it has additional components which impact performance. So why would I use Cassandra for vector data? Cassandra in general, as a database, currently one of the largest deployed databases in the world based on the amount of data that's being held. So if you have not heard of it, it's widely adopted. It was created by Facebook by taking BigQuery from Google and DynamoDB from Amazon, created Cassandra. And the benefit of Cassandra was that it was able to scale linearly, which means that as your data grows, you just add more nodes to the cluster. The data replicates in multiple locations, so you can have a set of data in the US, set of data in Europe, and it maintains their replication.
is quite resilient for that purpose, because if you have one node go down, or you can have two nodes go down, depending how you configure your cluster, you have no impact whatsoever. And so when you're dealing with data that you want to retrieve at any time, anywhere, quick, fast, you are able to leverage the basics of Cassandra to do so. This is not new to Cassandra, but on top of that, Cassandra added the vector storage capability. It's also free. It's an active open source product that you can go and download and install straightforward from the Apache organization. And one of the features that were implemented with the latest version of Cassandra, which is Cassandra 5, is storage attached indexes. This opened up several capabilities for Cassandra, one of which is now we're able to store vector data and index it so we can retrieve from it, as well as the type of storage that was now used is whenever you write to Cassandra on a table, and the table has a storage attached index, that index is updated on insert. The benefit of that is that there is no batch process that lags the insertion to keep your indexes updated, so your vectors are always updated as the data is inserted. This is a big differentiator between Cassandra and some other databases as well. So what did we do before Cassandra 5? So let's say you have a set of text that you want to store in a database. You could take that PDF document, for example, run it through a fast text, which is a model that will give you the embeddings with the data processor. So you have in Cassandra, it looks at the file, takes out the text, finds out what the common attributes are, and then you can store that set of data as text in Cassandra. The problem with previous versions was that you were not able to do a proximity search. So you had to actually retrieve the full set of data from a record to be able to do a comparison on the metrics, on the vectors. Not a good idea, especially when you're dealing with large amounts of data. Could it do it? Yes, but not ideal. An evolution of that was to leverage, for example, open search. So you could store you could generate your vectors with a data processor, store the vectors in open search, and have a key that is attributed to the metadata that's in Cassandra 4. So you do your query, narrow down which keys that you want from within open search with the KNN plugin, and then take that data to Cassandra and pull it. So again, not ideal. Now today, you can take a document, generate the vectors, store them in Cassandra, and then query against Cassandra directly. So Cassandra, what can you do with Cassandra 5? Vector storage, we covered that already. So data is indexed on insert. And so with a number of other databases, there's a lagging process for indexing. So you'll have high CPU, high resource utilization for rebuilding or reorganizing the index whenever you're inserting data, that it would impact anybody trying to read the data. So having the index as part of the table, we're avoiding that with Cassandra. Another feature Cassandra 5 implemented is the approximate nearest neighbor. It's maybe not as accurate as KNN, but it is much faster and gives pretty good results. In conjunction with the open source project called JVector, it also speeds up the process by compressing the data for retrieval of vectors. The size of the data that you are you can handle is really the size of your cluster. Cassandra being linear means that if you're wanting to store more data, you add more nodes to the cluster. You've got petabytes of the clusters with petabytes of data out there that people use with hundreds of Cassandra nodes. In addition to that, by having more nodes, not only do you have the capability of able to store more data, but also your workload is distributed across multiple nodes in the cluster. So whenever you do a query, your query is distributed against many nodes as opposed to a handful. Cassandra has a number of connectors, so also you can query Cassandra using the open source Spark connector, for example. So it becomes easier to query with Spark because yes, Cassandra historically has had the rigid data model, which limited the type of queries you could run, but with Spark and with storage attached indexes, that has changed quite dramatically. So, and again, it can be integrated with your RAG process. So, okay, is it hard to be able to store this data in Cassandra? Actually straightforward. You know, it looks like a simple SQL create statement. You've got a create table. In this case, I called embedding image. I have a column. There's a few UIDs, a text column, and then the embeddings themselves is of data type vector with a float. And of 300 values in the vector, and some additional columns that you want to use for related values for the table. Once the table is created, you can see here I'm also creating an index on it, and it's a storage attached index. And that's all you need to have Cassandra be able to store your vector data. So if you're wanting to do an example of run an example for Cassandra, InstaCluster has a managed service for Cassandra that you can deploy, including Cassandra 5. You can deploy it on any of the 3 major clouds. You have the ability to create Cassandra using either the GUI, or you can have an API, using an API or Terraform provider to create and manage Cassandra, as well as monitor. In my case, I use the Terraform provider to create it. I'll show you an example of what it looks like when it's created, then we can, but, one more thing is that InstaCluster has other products other than Cassandra that you can use, OpenSearch, Postgres, and you see the list here, so. Okay, so. Let me see if I can switch the screen here to. Where is it here? Yeah, that's the image we're going to search for. Let's see. To move this window over. Not that side. Okay. Sorry, I'll be there in a second. Need to exit from this demo. Okay, and let's do one display. So that way I don't have to turn my head around. I'll do one display on my machine here. Let's see. Display. Okay. Got it. Sorry, can I have the phone? I need the MFA on my to log in. So, Instacluster NetApp Instacluster is secure. We require MFA for login. So. Okay, I'll just take 60 seconds here to briefly go over the console. I have, for example, here a Cassandra cluster. I can look at the performance of it. I can see the connection info once it's deployed, the IP addresses. I can have sample code of how to connect to the database, of whether you're using Python to connect to the database or you're using Java. It gives you examples of how to use it, so speeds up the process. Creating it is fairly straightforward. You can pick any of these products, but today we'll pick Cassandra, give the cluster a name, pick a cloud provider that you want to deploy at, and hit next. Pick a version of Cassandra that you want to use. We want to use 5, and add my IP address that I want to use, hit next. You get to select what type of EC2, because it's AWS, so you have multiple options, but we had recommended one as a basic one. You can control the replication factor, and hit next, gives you what your estimated cost would be per month for the cluster, and create cluster, and then you're off to go. So, but for this session today, and it's already being created. For the session today, I do have one that's already been provisioned. And so let's, unless I have any questions right now, I can go into the demo of doing a text and search, image search. Okay, cool. Okay. Is this visible? Too small? Okay. Okay. So using Python to be able to do this work, in this case, I have a Python notebook, and what we have is we're just setting up some directories, and then I'm downloading the model. So for the text search, I'm using fast text. And let's see. Well, actually, this is downloading the Cassandra driver, and this is where I connect to Cassandra. Here's where I specify the node IPs. I have that in a file. The username and password, I have it in a file as well. The ports where I'm connecting to. So once I have that established, I'm able to connect to my Cassandra cluster. Once I'm connected to the cluster, I have the ability then to say, okay, I'm going to create a key space within the cluster, and I'm going to drop the table if it exists, and then recreate it, create the index on it. And as you can see in my last run, the timing on these are fairly quick events. So 0 seconds, 2.3 seconds. They were not, and this is again from my laptop. Creating the table, and then after that, load some required packages for running the fast text embedding generator, and just some additional imports as well that are needed for Python. And this is actually where we I'm loading the fast text model, which is a Word2Vec model. This one takes the longest. It took 2 minutes to load it. So it's a 400 megabyte file to load. Next is in this. So here so we loaded the model. And then we built function to be able to convert the text that we're passing it, to convert it to a vector. And after that, we're going to do the actual conversion of the text and store it into Cassandra. So so we created an embed. That's right. Okay, maybe we're defining here. Actually, yeah, we're defining an embed into Cassandra. So what we're passing to that is the key space, the ID, the embedding itself, and the session that we had opened up to Cassandra. And based on the embeddings that were generated, I'm running an insert into the database as any other SQL insert that you're probably familiar with as well. Some exception handling and retries and so on and so forth. So this is where we've trained the model with, we've loaded the model already. Now what I'm going to do is take a file that I have already on my laptop, is the Cassandra Best Practices PDF. And I'm going to generate the vectors and insert them into Cassandra. And then I'm going to do a search. So in this case, we're going to find a similarity search. And based on that, the query is, again, a very simple SQL statement with just one bit of difference, is that we're going to order by the nearest neighbor for the embeddings that we have on the table. And if I run a query, let's see, am I still connected? I'm not connected, so let's see. Let me see if I can connect, and we do have the live portion. The Wi-Fi has gone down, up and down throughout the day, and last I heard was down, so that's why I'm kind of hesitant to run these individually, but let me try to connect to the database one more time. Okay, connected to the cluster. Okay, so it found several entries. Some were 100% match, and some others that were not. What I've done in addition to this is, let's see, I created a service where you can have where it queries the database. As same queries that I did before, I can do a search in, this going straight into Cassandra, running a search, and then waiting for the result and saying, okay, yeah, I found the text, you're looking for Cassandra. You know, this one is 100% match because it's Cassandra. And these are some other matches. I can then look at the word rack and see if that matches. And here are some of the results we get. So this is purely a Python service that is doing a query against the database and bringing the results back to the screen. There's no additional components in there. So, okay. I have one more demo, which is the image search. Any questions before I go? Okay, so this is a similar, a lot of it is similar. We're using a different model, ResMeds 50, and doing some Python prerequisites, doing some installation. I'm using requiring TensorFlow, importing the Cassandra driver. And if this is going too fast, I will share the link to this repo so you can use it if you will, and some of the slides as well. So let's see. The ResNet 50 is the data model I'm using for this image recognition. And the goal of this is I want to provide an image that is used to search the repository of images that I have uploaded. I have vectors created for 3,000 images, and it's going to do a search against that. So what I'm going to do first is I'm going to train my model with 300 of those images, just so that we can have a model established. And that was done earlier. And once I've trained the model, then I have an example here where I'm verifying what is the embedding that I generated for an image. So I took image 300D and say, give me the embeddings, which is the array, the vector, and here are the values. Again, connecting to Cassandra, same as the previous example, just standard database connectivity. Then creating a table. This one's called embedding image, so it's a bit different, but the structure is the same. Creating an index on it. And let's see. Okay. So declaring function that's we're doing here is an insert of the embeddings of 300 embeddings for this model, and then load some additional tools for be able to access the model to run. And this is where I'm downloading the images. Then the similarity search. So I'm going to search, again, simple statement with an order by of the nearest neighbor. So now I'm ready to do a search. I have several images I can search for. So if I can take this image here, for example. If I go to any browser, I can, this is, I went to Amazon, picked up an image to search for, and this is the result that came back. So this, to get this, so what we did is we had the 3,000 images, we generated the vectors for them, stored the vectors in Cassandra, then did a query, then we converted this URL's image into a vector on its own. So we have one vector to compare against the 3,000 vectors, and we did a query based on that. So it compared the one picture that we had with the other pictures that are stored in, vectors that are stored in Cassandra, and it gave us the match. So there are other images that we used. Let's see, if we do, this is what I looked for, and let's see if my connectivity is going to work. Yep. So it knew it was a red T-shirt, so it gave me what it can. This has a car, so it's an engine of sorts, so as motorcycles do, and so you can vary the image, and gives you different results based on the image that you're looking for. This one, I think this one was the least match, but let's see. It was tough to find this one. No, I had looked for a bear earlier. You probably saw the picture of the bear earlier, but that one. So again, with this one, we're using a simple Cassandra search to be able to search images for some values. Yes, sir. So use the published model, which is the ResNet 50. Oh, sure. Yeah, let's get the microphone there, please.
What type of attributes and information are you using to embed the actual vector information of the image in order to like find similarities?
Right. So I'm not doing anything. I'm just using the basic ResNet 50 model, which was developed by Microsoft. And that's tweakable, but again, depending on the use case, you can use different models to, to better generate the embeddings based on the criteria of the images that you have or the criteria that you want to get out of it. But once those vectors are created, they're stored in Cassandra, and Cassandra can then query them based on proximity. Mm-hmm. Yeah. Right. Correct. Correct. Mm-hmm. Mm-hmm. Okay. Yes, sir.
Yeah, I saw a function you call reduced dimensionality. So what is that function doing underneath? And why do you need that?
Let me see. So I'll get back to that. My guess is, and purely my guess, so this is a colleague I worked with that to generate this code. So the idea is to narrow down the image based on what is available in the image that it calculated, and try to narrow it down to the set of vectors, which is the dimension of the vectors is basic dimensions, to reduce the range of what this image can be.
Yeah, okay.
So that's my guess, but...
yeah, if you can tell me whether you're using principal component analysis or something like that to reduce the dimensionality, that would be good. Okay, thank you.
Yes, I will be sharing the deck and the code as well.
Hello? Yeah. So I have a couple questions. So what is the uptake? I mean, are you using the pure open source version of this? Okay.
Absolutely. Yes. So
sorry,
go ahead.
Yeah. Well, the question is, okay, that's answered. In comparison to things like Couchbase and some of the other kind of document or text databases, what is the uptake? Do you have any idea?
Sure.
People are going to it because, forever this is like the perfect or one of the most perfect uses for it. Because when a lot of these came out, I said, what a waste, relational databases are getting so good and fast and all this. Yeah. So who needs this? So, yeah. So if you have any idea if you're competing with them and what the relative uptakes are.
Sure. I think it is use case dependent. If you're already using one of those databases and what you're looking for is to augment it, do some searches within Couchbase or within Postgres, that would work. Where we find that this becomes much more useful is where you're leveraging the key features of Cassandra. Is the ability to scale to a large size, its ability to get results fast because it's parallel, the ability to make sure that the database is consistent and reliable. Okay. Yeah. Right. So in this case, it is the storage attached indexes, which is updating the indexes on insert and not batch, which many of some other databases and with different versions they have modified, but some databases do not update the indexes immediately, and so that's a big difference, as well as the J vector, which is it's the implementation of a disk ANN functionality by Microsoft to speed up the search for the vectors themselves. So by compressing the data and quick access to vectors within the data set. This is pure open source. Yes, yes, yes. So the models are pure open source. I'm using open source Cassandra. I am using the InstaCluster managed service for Cassandra, but underlying that is a pure open source Cassandra, no modifications, no licensing. Yeah. No, no, no. It's very useful for sure. Yeah. Any other questions? Excellent. Thank you very much, everybody. I'm sorry. I'm sorry. You're correct. I was in my mind. Sorry, I was going to email it. Or yeah, let me. Is there a way to send a? I'm sorry. No, so the document, the notebook, is something I have, right? I want to give you the notebook. I'm trying to see how I do not have it in public repo, but I want to have it in public repo. But the question is, how do I pass it later on? So we are. I apologize for doing this, but we are in the booth 103. Actually, you know what? Here, if you'd like to get a copy, I'll put my email up there. I think that's probably the easiest way. I was just took a second. Okay, okay, good to know. So, yeah, actually, I do have, yeah. So, well, before I get to there, just one more thing I wanted to cover. So, as I mentioned, InstaCluster is a part of NetApp. And we provide the ability to create any of the products. Let me put a full screen on this. Yeah. Any of the products below, whether it's OpenSearch, Kafka, you're able to create any of those on the cloud or on-prem. We provide the managed platform, but if you're already running these products, we provide support. So many people are hesitant about using open source because they don't know who to call. InstaCluster is there 24/7. We have committers on many projects and submitters. As well as we do have consulting if you're looking to look if this fits your use case. Please feel free to reach out to us. And let's see. I'm trying to click one more slide. There we go. So that's my email on the bottom. Please feel free to reach out to me. I can send you the link to the GitHub repo. And you can also visit us on booth 103 if you have any questions regarding our services. If you do go to instacluster.com, you are able to set up a 30-day free trial, so you can create your own cluster and run these demos on your own. Yep. Thank you.
Hey, hey. Can you hear me?
Here, hold it here, and then maybe you might
Hey.
need the mic closer.
Hey, hey. Hey. Can you all hear me? Yeah.
And then bringing the mic closer to you.
Can you hear me? Can you hear me better now? Hear me better now?
Some people just tried like bringing the mic closer.
Yeah. It's also to be able to drink. Hey, can you hear me better?
Your name is just Thomas Charlin?
Yeah.
Okay. I want to make sure.
French name.
French name? No, that's good. I wanted to double check because it's like, I'm pretty sure Charlin is not his last name. How long were you planning on your talk?
Like 40 minutes and questions.
Okay, yeah. You have an hour slot. You know, take as much time as you want with that one. As soon as you're done, whatever remainder time is left, I will, just turn it to them for like any questions and whatnot. But yeah, as long as like if you're gonna reach like maybe like I guess 10 minutes before the hour ends, I'll just flag you down saying, oh, you have 10 more minutes. But otherwise, again, take up all that hour you want, and then like again, when we have time, I'll just like give the mic to the audience for like any questions and stuff.
Sounds
like
good.
that. But yeah. Okay.
Cool.
Good to go again. Like, yeah, I'll get you started like around 5 minutes from now.
Thanks.
If that mic doesn't work out, I'll try to switch you over to this one. Maybe this might be a little bit easier.
Yeah, sure. It's fine, thanks.
Good evening, everyone. I'm here to introduce Mr. Thomas Charlon for his presentation, which afterwards there will be a quick Q&A. But yeah, I'll hand it off to him.
Thanks. Can you all hear me? Is it okay? Okay, great. Thanks everyone for coming. Maybe I should have precised in the title that is actually local LLMs that we're going to see. So we're going to use easy tools and build up the pipelines ourselves. There's some maybe much more bigger tools that are starting to be developed to do these, but it's always good to have a sense of how to do it with easy tools, small tools, yourself. So pipelines for biomedical semantic search. So semantic search, vector search, it's all kind of same thing. So just a bit of background, computer science engineer, bioinformatics PhD, self-trained in NLP. I did a bit of Twitter withheld content analysis. 3 years wannabe founder, web app for real estate market, and a bit of storytelling also. So I joined Harvard Medical and Professor Tsai, January 2024, research associate. So what they do at that lab is translational data science. Name is learning a health system. And what we actually do most is analysis of electronic health records. So hospital visits, codified data when you go to the hospital, diagnosis performed, the medications prescribed. That's all the data we're looking at. A big part also is the clinician's notes that will detail a bit why some diagnoses have been performed, why some medications and not others. Can be insurance reasons, it can be side effects, estimation. So one of our big collaborators is Mass General Brigham, one of the leading hospital in Massachusetts, and we also work a lot with Veterans Affairs. We have 3 main disease we study: rheumatology, multiple sclerosis, Alzheimer, but we also do methods for general biomedical that can be applied to any kind. And one of the big research area of my professor is transfer learning from large to small hospitals. So when we have a lot of data from the large hospitals, and so to enhance the information we can extract from the small hospitals, but while still maintaining patient privacy, data confidentiality. So I was employed to work half-time on suicide prevention project and half-time on lab level and multiple projects. So for suicide risk prediction, we're trying to help clinicians follow up in priority with the at-risk patients. And so we use codified data I talked a bit about and NLP on clinicians' notes, which helps a lot, especially in the mental health areas, but also in general diseases. So some of the 3 things I've been doing, apart from that on the lab level, is a dictionary codebook where we map hospital variables, local variables to standardized classifications. So this will be the ICD, International Classifications of Diseases. And I also do a lot of our Shiny apps with JavaScript. I enhance some of their apps. And so since I'm a bit of industry pharma background, I know a bit of quality processes that helped quite a lot. Reproducibility for me is quite a big thing. Open science, like open data sets, all the way to Docker image. This is a little example of a talk I gave last year. Here's a QR code to my website where you can find the talks. Some of my writings will come back to the QR code. So here what we see is the correlation matrices between the concepts. So we have the diagnoses, and so with these kinds of graph, we can investigate. It's kind of a research-based app for us to make sure that our models are working correctly. This is not the kind of things we'll show to the clinicians directly, but it's more for us to troubleshoot our methods. This is an example of the dictionary codebook I was talking about. So this is fiwascatalog.org. It's a resource that we use. Here we have the ICD classifications. So we have a lot of different classes, a lot of details. And we have what we call a fee code, which will be the more broader group that we will actually analyze to have statistically meaningful groups. So this will be a big part of my first part. I've been doing this semantic search on these kind of dictionary codebook. So it all started when my professor asked me, oh, could you do us an Elasticsearch embedding-based app? So I didn't really know what that was at the time. And since on my resume it was written that I did things with Elasticsearch, she knew that it would be a great match. So I found this cool blog post, Dylan Castillo, which I highly recommend. Maybe the only troubling part is that it uses a virtual environment and not Docker, and that cost me quite a lot of time. But so here you have a bit complex diagram, but what's going on is, so you have the browser, user, that's the web app that the user accesses. You have the vector database, the indexer, the documents. So documents is what we're going to search into. We index them, we put them into the vector database, and the search app retrieves them from the vector database. So you give a query, it looks at the closest documents, and it returns to you the documents. And that was kind of a nice moment for me. I haven't really worked with Elasticsearch. I heard that it would be useful to search on elements with many number of characteristics, but I didn't really get what that was meaning. And so I've been using vector embeddings to represent words quite a lot. And that's when I kind of make the match. Oh, so we could actually store the embeddings in Elasticsearch and query them directly. So I guess a lot of people are not really confident with embeddings. I'm going to give a little primer, very crude, but this should get you up and running. So in 2013, there was Word2Vec coming out, which made quite a lot of noise. And so the latest natural language processing are kind of similar. So imagine you have a paragraph, several sentences. Say each time 2 words appear in the same sentence, you give +1 similarity to that pair of words. You build up a matrix with each of your unique words, and you have your similarity values. And this matrix enables you to ask what are the 5 words most similar to word X. So this is symmetric matrix, similarity matrix. And probably you heard in a lot of the previous talks, they was talking about OpenAI embeddings, for example, that they were querying. So here is an example where you're building yourself these embeddings. It can be useful for data privacy when it's patient data. It can be useful when you want to train specifically on one kind of data. But most of the time, these big natural language processing methods like ChatGPT, when they train on a huge amount of data, that's when they get much better. So you can do it your way, but it's usually better to use pre-trained models. So like I was saying, ChatGPT, they're not really doing similarity matrices, they're rather doing neural networks, but they still provide these embeddings. So when you query OpenAI embeddings, it's something that they kind of reconstructed just for you to be able to use it. You can see it a bit as the last layer of the neural network, but it's not even really that. So why is it so useful? Because it can guarantee you no hallucinations. So my first scientific encounter was hallucinations. I was doing these embedding retrieval. I had these, so I'm querying obesity, it gives me 10 variables. Let's say overweight, anorexia, bariatric surgery. So like the next step would be, oh, well, can you regroup them? Do you see the commonalities between them? Because what we see is that there's synonyms, there's like a parent family of class, eating disorders, and more like medical consequences. And after maybe 10 passes, prompt engineering, asking my LLM friend, he's telling me, yeah, you should ask him to do a tree. Well, after a while, he starts including a variable that was not in the 10 that I was giving him. So this is inherent knowledge. But so it is quite problematic because even with a RAG system prompt, where you actually tell the LLM, use only the list provided, you're not even doing jailbreaking or whatever. It's just that since you're giving few sets of commands, at one point he just doesn't think that the first one was that important. And so my guess is that the more you add prompt complexity, the higher the risk of hallucinations. So when you're doing this kind of stuff, you want to keep your prompt quite easy, not too complex. These last days I saw some very big prompts, so I think it works, but depends on the use, and you need to be careful about that when you're doing new prompts yourself. So I'm going to insist a bit on this. Let's imagine a more like concrete example. You have a biomedical data set, you have maybe a few variables, 1,000 patients over some time, body mass index. You ask ChatGPT, here's a list of variables, which ones should I study to best predict cardiovascular? It will tell you out of the 300, these 3, and then you'll notice, but 2 out of 3 are not in the list. So this shows why we prefer to use embeddings in our methods. We have less natural language understanding. Negations are not managed at all. If you say not bipolar, it will just understand bipolar. But you have more control and output. You can make sure that everything you retrieve is in your database. So this is what the first app looked like. So the rows here are all the variables that I map to standard ontology and then to the group codes. So here you have the hospital code, standard one, and the group one. And so we have 1.4 million rows. So we give this to the pre-trained model. We build the similarity matrix. So it's actually a similarity matrix that we perform dimensionality reduction on it. So that's why we call it embedding matrix. And then we can query new words. So the cool example here is you type in bipolar and you get lithium, which is a known medication for bipolar. And what I think is a cool example here is that it shows it's not just finding synonyms, it's actually finding treatments. And so this is BGE based. BGE is a model from a Chinese team. In literature, it shows it's quite often very good, better than most. And my talk will be especially about how I compared BGE to other models, how I built a pipeline to be able to easily compare all these models, and so for my dictionary app to have the best embedding model that I can find. And so these are pre-trained models. Compared to OpenAI embeddings, you won't need to buy anything. You don't need to pay each token. You just need to download the model once. So little schema, 1.4 million descriptions. We first do the indexing. That's where we're going to use PyTorch, LangChain. We put it into Elasticsearch. Each of these descriptions has representation of 1,000 numerics. This is all stored in Elasticsearch. It weighs around 15 giga. And then for each user, query a word, do the representation on the fly, do the cosine similarity with your database, find closest words based on the representations. So PyTorch enables you to index with your GPU, but LangChain is quite important here to enable vectorization. So computing a word, or so usually I will have maybe sentence length descriptions. In previous talks, we talked about how should we chunk documents to do the embeddings. So here we don't have this problem. We're just doing small. And so each representation is computed fast, but our problem is that we have a lot of representations to compute. So if you just do a for loop, your GPU will be really underused. And that's where vectorization and LangChain is really useful. And so these descriptions, I index them in 25 minutes on a low-grade GPU for $300. But get things right with a for loop for start. And so once you index this, you can use the Elasticsearch functions. There's native functions to perform cosine similarity. You're not going to need to bring up your whole matrix in memory. You can do this basically on 8 GB RAM, even if your similarity matrix is much bigger. I want to show a bit that the code is quite small. There's a lot of redesigning that goes on. Keep it easy. The cool thing is LangChain. So here we have the function Elasticsearch store from documents. So you basically give it your list of documents, your embeddings function. So this will come from Hugging Face. You download it with this. And this is basically everything you do. This stores it up in your Elasticsearch. You need to have your Elasticsearch instance running up here. And this will populate your similarity matrix in your DB. Here we see the Docker compose. So the upper part is where I define the Elasticsearch, and the lower part where I define the indexing. Here you can see I'm deploying with a GPU. The build refers to this Docker file, also quite small. So I just install a few Python libraries, Elasticsearch, transformers. And so Docker Compose is really useful here to be able to connect to the Elasticsearch instance easily. And once all this is done, I come back to my RShiny app. I prefer to develop in that. We can write quite complex web apps in very short source. And so this is like how my web app is actually coded. And we have our package that does the interface to the Elastic database. And I actually first do the indexing on my local computer. Then I populate my server with the pre-indexed database. And I open the RShiny app on AWS. And this is where the fun begins. Because one model is all fun, but what about the other models? Some other models are trained only on biomedical data. Shouldn't that be better? Well, looking manually, we can see that BG is still better, but there's even more, like SAPBERT. And this time literature actually says it should really be better, but we don't really have convincing benchmarks, like easy to reproduce code. So that's why I kind of took this path of, okay, which pipeline am I going to build to be able to do this, to be able to compare maybe 5, 6, 7 models. And so I already been using a bit in our laboratory. We have known pairs. So it can be clinician created, so expert knowledge. We'll have things like first concept, schizophrenia, related to second concept, psychosis. And how we measure our prediction model's performance is that we query schizophrenia. If the top matches, maybe 10 first matches, have it, then we say, okay, it's good. So this is like the easy way to explain it. The more rigorous way is AUC. We random null pairs. This also helps us to find good similarity thresholds. And we can say, okay, at this threshold, we have 5% false positives. And for a clinician that's looking at this app, he wants to have automated ways to know how much variables to return. Because maybe one variable will have 100 variables related, maybe another one will have only 10. That's why we don't want to have a fixed number of variables we return. We want to base it on actual clinician usefulness. So this can be derived by clinicians. It can also be mined in scientific literature. There's different ways of constructing them, and it's quite important. I'll come back to it. And so this is our data set of true positives. But how is the actual design going to go? Previously, I had this two-step indexing deployment. I'd like to keep it quite close to my app to not have to have completely different environments. I already have an R package to do these models' performances. So this is where I start wondering in which way I'm going to connect all these components. I already have a Docker Compose calling a makefile. Maybe I could do a makefile calling a Docker Compose. Maybe I could put R in the Docker image, PyTorch in the R image. What I actually went with, let's just do a first makefile, root level, Docker Compose, and then other makefiles. So here on the right, you have the folder structure. First Docker Compose, ESLang will be the Python folder. Relastic will be the R folder. So like this, we keep everything separate. We have our PyTorch running fine. We have our Shiny running fine. We don't mix them too much. And in our makefile, we call our different Docker Compose rules. We first build our evaluation dataset, move it to Python, index, store it in ES with the Docker volume. And then from R, we can access the Docker volume easily. This is what the Docker Compose looks like. First rule will be this write evaluation. This will be the Elasticsearch. It's very similar to the one I showed previously. The indexing. And the new, where I call the kgraph package to measure AUC. Just call make, cat the text files in which it writes. Doesn't take more than a few minutes. We have something like 20,000 pairs. And we have these 6 models I'm comparing. So these are all pre-trained models. And this enables us to say, okay, highest AUC is the one we want to use in our dictionary. And we can take it a step further by investigating a bit our pairs. So in our pairs, we can have diagnosis relationships, such as what I was saying, schizophrenia, psychosis. And we can have medication diagnosis, like bipolar lithium. And what we can see is actually all these models, they perform much better when you're doing just diagnosis to diagnosis. And when you try to predict a medications that used to treat a disease, it's much harder. And so it's kind of related to synonyms, to pairs that are similar or related. And what we usually do in our lab is that we have knowledge graphs that enables us to get better performances on these non-synonymous. And a lot of the time, the diagnosis to diagnosis relations will be almost synonyms. Wanted to touch base a bit about fine-tune BGE. One of the limitations I saw when I was typing for schizophrenia, so maybe we had 200 variables returned. And most are good, but we also get some strange outliers, bacteria, leukemia, pneumonia. There's a common thread here. It's the suffixes, and so it's because of tokenizations. It's because of how these neural networks work. Because they're kind of breaking down words in smaller chunks, taking roots. And so for very common word, let's say happening, they understand that ing is, there's happen and there's ing. But for more rare words, so like the more frequent the words, the more it finds the commonalities. And the less frequent, the less it will treat the word as just one big word and not decompose it. That's how they kind of do character level without really doing full character level. They chunk up words as it's more and more important. And so in practice, what we get is that the more rare words, they're considered similar just because they end by the same letters. And so I heard a bit about fine-tuning these last days. Some people were saying that it's quite expensive. There was even in specific teams some debates on should we do it or not. There's also some consideration on are you taking the model out of its first course? Are you biasing it too much? Are you overfitting? And so we tried also a bit, tried inputting a lot of biomedical pairs, fine-tuning, but I mean, I think one of the fundamental limitations is that the original teams, they had quite a lot of resource. They trained it for 1 month or more, and you're trying to do in a few weeks GPUs. So it's quite hard to do something better than the original team. But if you focus just on the errors you notice, then that's where you can do actual fine-tuning that will give you a better performance. So I did this with our intern. In my latest dictionary app, we're now using the fine-tune BGE. It was like all the different methods we tried with a lot of medical pairs were not really working. And the only thing that worked was when we were just focusing on words with common suffixes. So this is the app that came out of my intern Joseph Hosch's work. So what we're doing here is clinical trial search. Type in a condition, it will give us the clinical trial. So this is just an API call. But the more interesting part is that we're embedding the title and the summary. And then we're going to query PubMed articles. So we're fetching publications that are similar to the clinical trial that we want to study. So This one was menstrual cycle and weight loss. And in the publications, you will have menstrual cycle and weight loss related publications. This was first part, half an hour. And so this was like my pitch for SCaLE. One of my first line of my abstract is that, oh, well, hallucinations is really a limitation. Let's just use embeddings. But my most recent developments, I'm actually using Llama. So I had a new use case where Llama proved really useful. So it's a bit similar, but a bit different. So unified medical language system. Here this time we have a dictionary of 5 million codes and descriptions. And we'll have a lot of, for one code, the different ways of saying it, like the synonyms. And it can also have the plurals, the acronyms. And in these codes we have relationships. We can have more or less complex synonyms, parent-child. So usually what I was saying about the standardized code and the group level code. So usually the more detailed codes will be the child of the group code. And so we're using this quite a lot on our clinicians' notes. And one task we're spending a lot of time on is to do roll-up of these codes, because some are very specific, and to analyze them usefully, we need to regroup them in larger groups. So I'm using Llama, which is Facebook's open source version of ChatGPT. Open source in the sense that it's a pre-trained model that you can download. So UMLS, 5 million codes, parent-child relationships. So I told you my research project is suicide prevention, so in this part we're going to focus a bit more on this. Here's an example of parent-child relation. One of our complexity is that we don't really know at which level to stop. We could use the frequencies to say, okay, now we have something that we can use statistically, but it could also be cool to have a study-independent dictionary that we can just use without needing to go into our data. And so this parent-child relationships, the graph, enables us to do a first, to understand the structure of the variables, but it's hard to really regroup them in meaningful groups. You can use graph properties like subcomponents, so basically the number of child one node has. Degree will be the number of inputting edges. And so first experiments was decent, but you get very small groups. It's not really ready for use yet. So I started taking another pass, guiding this roll-up with the codified dictionary we saw before. So we already had like schizophrenia with acute disorder would roll up to schizophrenia. So we're going to say, okay, these are the group levels we want. This will guide us. So what I'm doing now is start by finding the exact strain matches. Then we use the synonyms and the parent-child relationships. But even then, we only have 10% of the 5 million mapped. And so within those 10%, one of the most important things are the fee codes, the group level diagnoses. And for them, we have more like 60% mapped. So quite good, but we still have a bit to do. And in particular for my field of research, so one example why it didn't match with the exact string match will be because in the fee code, it was saying suicide or self-inflicted injury, and the QE will be N. So it's not very far, but we do have to be careful with partial string matching. We don't want to map type 1 diabetes to type 2. Another core problematic, this is an example of the suicide fee codes. We basically have one group, either ideation or attempt, and then two subcomponents, the ideation and the attempt. And we want our QE mapping to follow this hierarchy. And with the graph properties, I could get good mappings, but I would basically have the same QE for the two fee codes. So that's why I finally gave up on the graph properties, starting taking the llama road. So we have the risk of hallucination. We're not going to do it on too much. We're going to quality control it so roughly, but I actually discovered it's not the worst part. So what we can do is we do a first filter with the BG embeddings I was talking about. So we get 30 most related variables, and we input this to LLM. Which one is the best match for the string we're trying to map? And so giving this to Ollama in the terminal and ChatGPT in the browser, Llama gave me suicidal behavior, which was actually the one I was trying to get. ChatGPT suicidal ideation. Was quite impressed that Llama was doing a better work. So this is 3.1, 7 billion parameters. But the thing is, LLMs are not really reproducible. Once integrated in Docker Compose with the API call, oh, so sorry. Here's the hotline to talk about your thoughts. Or other variants of that, or the word I was not looking for. And so one of the things we're talking about is that temperature parameter will lead your results to be more consistent, but I can tell you that from my experiments, it doesn't work. So I was kind of stuck on that. But I was still quite impressed by the fact that I found the suicidal behavior one. So since I saw it working once, I knew I could do it again. So one of the cases that was annoying was that he was giving me suicidal ideation. Here, one of the big step that enabled me to move forward, you include the variables that you actually don't want. Here's a list. You cannot use these variables, and you enter the text descriptions of the variables you don't want. So in my prompt, I also say, like, answer just this, nothing else. And the safety answers, managed with a few loops, kind of manually done. And I had one other safety error related to violence towards women. So it's actually just like a diagnosis of gynecology related, but the LLM tells you, I can't help you with that. So to be able to just, like, since I'm going to need to quality control all these mappings that the LLM is doing, I want to do most as I can myself, classic methods like string distance. So I'm applying this on the lower level, and then as I go up in the hierarchy, that's when I use BGE and Llama. So I use it to do maybe 300 fee codes with 10 loops. So the two safety errors are the ones that require me to do the loop, basically. At the end, I'm still stuck on one that has an hallucination. So it's telling me, yeah, it's this variable, but it's not the variable I gave him. But it's not really a diagnosis that is so relevant either to me or very frequent. So I'm leaving that to someone else. So it works for me. And for me, the word of the end is that it's actually more about the safety than the hallucinations. The LLM will stop you, and you have to find ways to still ask your clinical questions. Few notes, takeaway. So semantic search, embedding based, vector search, it's all the same thing. The first part of a RAG, you have hallucination-free guarantees. To use LLMs, you'll need to constrain and control what it's doing, do as much as possible with classic methods. Even after the LLM did its part, there's kind of a post-processing step. And these known pairs and benchmarks, very valuable. I think they will become more and more. It takes a lot of domain experts' time. You can imagine that clinicians have other things to do. And often I think that when we see benchmarks on Hugging Face, we really need to think about, is it relevant to real world needs? What's the quality, what's the difficulty? Because, so we have models that say, okay, I'm better on this, but will it actually have an impact on early diagnosis? Will it actually give better treatment recommendations? And so I think there's still a lot to do on building these known pairs and these benchmarks. I think that these LLM parameters, there's so much, it's starting to become like a computer system. You can hardly find anyone who knows from top to bottom. In our lab, we have some deep learning experts that are used to play on learning rate, but the LLM experts, they just use always the same learning rate. So this is an example of parameter that some people vary, some people don't. And so there's a lot of different components, and the LLM experts are really doing text-based. And deep learning can be for images, for audio. And so I think that as we move on, it will be harder to get a full grasp of what's going on. In Llama, from what I saw, I think there's maybe 5 parameters that influence reproducibility. I just tried one, temperature. But so for me, that's really a hard problem, other than using a loop to converge. I really don't see any way forward. And so if we think about FDA submission for drugs, where we really need high standard, rigorous, reproducible, I think we're still a long way to making these LLMs useful for these kind of applications. So you really need to think about which of your application can make use of it. Because a lot of questions will just give you hallucinations. If you ask ChatGPT about some very new thing, about something that didn't come up yet, it will tell you, yes, I know about it, here's all to know. One good example for me is when you ask to him about books. It can give you parts of the books that are really not there. And one of the new things I saw in ChatGPT is it's actually starting to include references. So I think that that's an important way forward. When it tells you that one drug is related to one disease, you can actually go back to the PubMed publication. So we need to constrain and control what it's doing. I see a lot of new hires that just copy-paste. For me, it's very different from copy-pasting from Stack Overflow. Maybe not so much, but I do think we need to think about it like Wikipedia, like we need the reference. And so of course you're not going to go back to it, but you need to know the rules to know when you can break the rules. Thank you all.
We'll open the floor to questions now.
ChatGPT is pretty good for convergent thinking. It has some difficulties on the outer edges when you get into divergent thinking. The large language models are trained on, the data sets that are out there, and it doesn't take into consideration it doesn't do a contrarian view. And I think that that's probably where we hold that niche to think, okay, so this is what we got. Are we missing some of the parameters? Can you speak to that?
Can you?
I'll use an illustration. Okay, I'm a divergent. And so let's say I'm in the open education field, and I say, okay, I ask ChatGPT, what are the ways that you can get your college degree? And it invariably never says the way that is currently available from edX and Coursera, which I had a hand in. It never enters that into the option. So what I mean to say is that anything that the models have been trained on, some of the research that's been done, Wikipedia, all these other types of things. Do you have a way to correct for the fatal flaw of AI in that particular area of, basically creative thinking outside the stupidity, outside the group, outside the box?
Yeah, so I think there's two parts. There's the part about the novelty, and the part about the like more marginal. And so the novelty is kind of hard to fix because the model is trained at one moment. So you can do fine-tuning to keep it updated. The more marginal aspect is kind of what we're trying to do here, where because these, we can imagine that the general corpus on which it's trained, the relevant parts to biomedical labs are very small. And so I think that it will depend a bit on the models, and that's where we're going to need to do performance measurements and to find out which models just find the biggest groups and which models can find also the outlying groups. Yeah, so he's asking about like we're still talking about 1 million students. It's not really small groups, but when I say small groups, I'm meaning smaller than the other big group.
So you mentioned multiple models. Have you thought about trying some of the uncensored models that are out there to see if it gets around the safety issues? And beyond that, what sort of next steps would you want to go to with this research in the same domain or in different domains potentially?
Yeah, so the safety, I was a bit surprised. I thought that I would have less problems like this with local LLMs. I'm not so sure how to remove it. I heard about paper Bad Llama, for example, that was kind of saying that it was able to strip off the safety layer. So I think that's one of the way forward for that. The second question, where I'm going forward with this. So my big research project is suicide prevention. So this is what I'm currently focusing on. One of the, so this CUI dictionary is still kind of early stage, and I'm going to use it. And so I still have a bit of work to do on finalizing this use. This is the first time I'm using LLM to actually make the work. The BGE part was I've been using it for a few months. So one aspect we're investigating a bit is adverse effect predictions.
Hi, I had a question about the while loop that you put llama in. Was that inspiration from NVIDIA's technical report about putting DeepSeek in a closed loop verifier?
What was the first part?
Oh, how you put a llama in a while loop to get better results. Was that taken from NVIDIA's technical report on putting DeepSeek in a closed while loop as well?
No, it was just that I was noticing that it was giving me not always the same response. So what I do is that at each loop, I try to map it to my variable. If I can map it, then I take it out from the remaining ones. It's like every one that I can't map, I keep him into the loop until I find a mapped one.
Oh, so are you using like another model to verify that when it's sending its output? Are you verifying that with another model and then sending it back to the model to like reformat its response?
No, it's the same prompt, exact same prompt I resend to Llama.
Okay, thank you.
Thank you, very impressive talk. I have a question at the end. You mentioned there's still a long way to go for biomedical LLM to be very useful in the industry. Do you have, in your opinion, I think you already demonstrated that the model is performing pretty well. In your opinion, like what is the biggest obstacle in the field? That is it like the data is limited or privacy issue or the regulation that still makes it a long way to go?
So not the privacy issue is taken care of by the fact that it's a local LLM. I'm more concerned about the reproducibility. What I was saying was that maybe by doing these loops, by converging, maybe it takes care of this reproducibility. But like I had one example where I just couldn't map it. So if I was doing it like manually, so I still got my results, but maybe it wouldn't have converged. Basically, I would have still kept trying to map that variable. And so if you need to have human input that may be biased, if you like FDA wants to be able to reproduce your analyses, so that's not something you can ask them. Like, oh, if it goes on 20 times, just remove that variable from your data set. That's really not the way you can do things.
That makes sense. Thank you so much.
We have time for a few more questions.
Thanks for the talk. My background's not in biomedical, so I'm interested when you're talking about the dictionary that defines the relationships and how it doesn't have that much coverage, or that's kind of like a challenge for you for semantic search, which makes a lot of sense to me. What do you think is being done or could be done to build something like that that can be used for the whole community? Or is there some focus on that, or is that just something right now that is a little bit insurmountable in terms of getting better data relationships defined?
So especially for the mental health, it's a bit complex to put in very neat boxes, and a lot of psychiatrists are talking about multidimensional, like gradient-based diagnosis, basically. Like you have autism spectrum disorder. It says spectrum because it's like not really a clear diagnosis. So I think that especially for mental health, it's we need to have more fine-grained, And so the second part you're saying about the relationships, I feel that these relationships are quite basic in most. Like if you say schizophrenia related to psychosis, it's very like low level. And when you start to say one medication is related to a diagnosis, you start getting a bit more complex. And I think that there's actually very little of these complex pairs. And so for me, that will be one very important way forward. So it takes a lot of time for the experts, for the clinicians to take time to do that. But I think it's really important.
Yeah, I work in defining data relationships. So I guess my question is really specifically like, is this something that people are working on? Like those subject matter experts, are they building that for the whole community? Like, is that kind of a project that's going on beyond maybe your particular project? Because it seems like, yeah, it's obviously applicable to your project and other projects as well.
Yeah, so UMLS is quite a huge project. There's a whole field of ontology learning. So it's basically the word is ontology, and you can find a lot of resources on that.
Yeah, I have 2 questions that are like, it's very possible you explained this and I missed it, so they might just be quick clarifications. But the first was about the reproducibility issues you had with Llama. I mean, I assume you were using like a larger Llama model, but I know for some of the smaller ones, like you can self-host those, and there are things like Llama CPP, right, where you presumably can see exactly how like, although, you know, I haven't actually bothered to like look at Llama CPP and see what's going on in there, but I assume it's possible to see like exactly how every single calculation is being done and what the parameters are. So I'm wondering I guess I'm surprised that it wasn't possible to just get deterministic, like the same output. Like, could you speak a little more to like what the issue is with the reproducibility there and what would be needed to solve it?
Yeah, so a lot of people say that it's temperature, and what I saw was that it's actually not only temperature. And so I'm using 7 billion llama, which is kind of a small model.
Oh, yeah.
I'm using it local. Okay. So I could go into the source and figure out everything that's going on, but it would lose a bit the objective of winning time. So from my, like the latest things I've been looking at was, okay, what would be the other parameters that could influence this, that I could fix, and what I saw was that there's 5, at least. I mean, like from my understanding, maybe these 5 could, and so this will need further investigation.
And then my second question, which you I think might have answered, and I apologize if I'm just asking somebody else's question, was to do with embeddings, because my understanding is that there are like llama embeddings and like a lot of, like when models are openly released, like, you know, especially open models, like you usually can like get a vector model out of these like large language models. And so I'm wondering, if I understood correctly though, like when you used Llama here, you used it for its like generation, like to generate answers. I'm wondering like, is that a thing you're interested in doing, like using the embeddings for like a newer like large language model instead of the other models that you were using?
Yeah, so with the pipeline I talked about in the first part, it's a model we can easily plug into. So I've been focusing more on models that have been fine-tuned on biomedical data, and BGE in the literature was saying that it's quite good. So maybe rather comparing to commercial, and OpenAI has some good performance. So you need to take into account the cost of the tokenization, but maybe it can be worthwhile for your research. So it would rather be, I mean, we can try Llama. Let's see, but For me, in my guess, I think BG is quite good. Maybe with Llama we would get a bit better, but probably not much. But however, with commercial embeddings, we could probably get a lot better. And after that, there's a question of fine-tuning, how you fine-tune. So I talked a bit about fine-tuning with suffixes. You can also do similar thing with the prefixes. And
Unfortunately, that is the time that we have for questions. Sorry about that.
we can talk later. I'm happy to answer.
The next presentation will begin around 5 p.m.
Check 1, 2. Check, check. Check 1, 2.
Z Yasso. You can if you want. I am the senior cloud whisperer at Tigris Data. Tigris Data. I know.
Like yesterday, at different times, and so that's why he gave us extra batteries. Just in case.
don't mind.
Good evening, everyone. Here to introduce Ji Yaso, Senior Cloud Whisperer at Tigris Data, on their presentation. I'll hand the floor off to them.
Okay. Hi, I'm Z. Today, I'm going to talk with you about the wonders of AI agents and how you can run them with whatever model you want without breaking the bank. So let's start out by imagining something. Imagine that this is you. You wake up one day, you go to a meeting. Your boss is there, and he's insisting that your product needs to have AI, but there's one small problem. What does this mean? Like, well, let's assume it's something sensible. Like, maybe you're not a company that sells bottled water, but there is something sensible that you can do with AI. But the mandate has come in from heaven, and now you're the one that needs to go and implement it. You're probably asking yourself questions like this, like, okay, so I have to make AI happen. What are the moving parts? What can I buy? What do I need to build? What are the pros and cons of different infrastructure setups? When your boss talks about things like AI agents, what does he actually mean? And most importantly, how can I avoid spending a lot of money on this? Thankfully, the AI agent question is easy to answer. An AI agent is just a model that has access to tools like escalate ticket or run SQL query, or maybe even something as banal as drawing an image. The rest of the hype comes in from square peg, round hole to existing things like ETL nonsense with MuleSoft or other boring things like that. But really, when people say AI agents, just think square peg, round hole. So if an agent is just a model with access to tools, how do you make that happen? Let's look over the moving parts of AI. To keep it simple, I'm going to break it into 4 parts. The first part is the model. A model is fundamentally a big ball of floating point numbers that just happen to be the results of a bunch unimaginable amounts of text going through them. These models take input, turn them into tokens, turn those tokens into embeddings, do whatever the hell CUDA does, and then get you new tokens out the other end. Those tokens usually happen to correlate to words. There's hundreds of models out there, but if you're in luck, you should try, but if you're in doubt or don't know where to start, you should try Facebook's Llama series of models, DeepSeek B3, or maybe even one of OpenAI's models. They're usually good enough to start out with. Next, you have the inference engine. This is the thing that actually runs the model. There's a few options on the market for inference engines, but usually you use something like Ollama, Llama CPP, or whatever the heck they do in Python. And you'll have an OpenAI API client that hooks into the inference engine, and you mostly treat it as a black box. But this is the part that needs the GPU to run and the expensive part. When you pay OpenAI or DeepSeek for access to a model, the part they host is the model and the inference engine. Now we get to your code. Your code is going to be the thing that sits in the middle, wrapping the front end around the AI model and doing whatever square peg, round hole you need from the input format of the AI stuff to the output format the AI returns and sending it off to the next layer. This is the part that's the most diverse and opinionated, so I'm going to cover it the least. And finally, there's the sparkle emoji button. This is the chat box that pops up when a user clicks on that sparkle emoji button, the tool that summarizes the meeting transcripts for action notes or whatever your CEO thinks he wants. And that's it. This is all the moving parts. The AI models get run by the inference engine, your code calls the inference engine, and then presents the results to the UI. It's basically the same thing as a database in the standard 3-tier web app architecture. When you get started, you'll see a setup like this. The example code that you're cloning from GitHub will almost certainly call OpenAI's API, pass the input and context there, maybe spin in a loop to handle tool calls depending on how it's set up. It'll have a UI that kind of looks like ChatGPT's UI because that's the hello world of AI stuff. You pay per million tokens. Like, let's be real for a second. This is probably good enough for most production workloads. Like, especially where confidentiality doesn't matter and you're not having to do excessive acronym compliance. OpenAI's SRE team is really on the ball, and it's super easy to set up. Like, all you need is a corp card and an API key. It works on any laptop or server with an internet connection, which in 99.9% of cases is all of them. It's easy to think about and easy to compartmentalize. You get access to some of the best models on the market, and it works out. Depending on how you use the model, what model you use, the phase of the moon, and other innumerable things, you probably will pay like $1,000 a month on the way far edge of the bell curve. You have to do some science, but that's what computers are for, right? Computer science. However, roses have thorns. And there's some pretty insidious ones that you may need to keep in mind that may make you think otherwise for this exact strategy. The biggest problem is one of the biggest advantages. You're relying on OpenAI or the other provider to keep the model up. This means you don't need to purchase GPUs or worry about uptime, but let's face it, one of the big providers being down, you're not the only one affected. But you're relying on them to keep the product functional. This is a huge position of power. They're selling almost all of the providers are selling their products at a loss to get adoption. Someday, the financial cows will come home along with massive price hikes. Like, OpenAI and other providers can and will deprecate that one model that all your production workloads hinge on. Like, this example is showing GPT-3, or certain snapshots of GPT 3.5 being replaced by other ones. And normally this shouldn't be a effectful change, asterisk, but sometimes it can have massive consequences in subtle ways on your app. One time I changed a model from one version of a model to another, and my chatbot went from, just happy and normal to a full-blown depressive episode. No, seriously. Imagine how much your app's behavior could change if, like, some key thing just goes weird. And then they send you deprecation warning emails. Raise your hand if you actually read deprecation warning emails. For the record, 3 people raised their hand. Yeah, see, nobody reads them. Suddenly, when things get actually turned off, it's your emergency. And you get to start learning about the joys of hyperparameters or having to have the dreaded conversation of, sorry, boss, sparkle emoji button's broken. It's out of our hands. Do you really want to hand over the keys to the kingdom to someone else? So, you're inevitably tempted to want to self-host all the things. After all, if the code is calling your server, deprecations are on your schedule, right? This is a nice idea. It sounds really good to the ear. Let's take a look at what the stack looks like compared to the other one. It looks basically the same, but it's a little bit different. Instead of asking OpenAI's API, you ask your own pool of GPU servers to run the model with the question and the context. The API endpoint transfer, it converts whatever you send into whatever the GPUs actually need, does whatever it does when mixing the pile of linear algebra around, and returns the results to get back to the user. The other main difference is that you're going to have to store the model somewhere because, like, a 70 billion parameter model at float 16 precision is at least 140 gigabytes of floating point numbers across n servers. That is big data. Like, officially, that is bigger data than most people's laptop RAM. That is the threshold for big data now. In practice, you'll probably end up storing your models in object storage like Tigris and then cache them to the inference server so they load fast. But otherwise, your app shouldn't really notice or care there's another model in the equation. You'll have some semantic differences, but really you can iron them out. It's just annoying when the semantic differences happen without warning. This is a bit more complicated than relying on a third party, but the strategy has significant upsides that can make up for it in some circumstances. Biggest one, most obvious one, it's your stack. When you're calling models on your servers, you own the stack. You get to choose what models are available. You get to choose the deprecation schedule. You get to mix and match models that will. Like, some of your app needs a model from 2 years ago. Great, you can do that. Something needs a model that was released yesterday. Assuming you have the hardware, what's stopping you? Yourself? No, what's stopping you is the amount of free time because you have to keep doing new features, eh? You also get to choose the models. You're not just limited to the ones that your provider has available. The ones that your providers provide are usually good enough, but what if you want to fine-tune a model for your exact use case or experiment with a new model like DeepSeek R1? What if you need to see the reasoning output in your flows? Many providers won't let you do that, but self-hosting, you can do whatever you want. Finally, the last big advantage of self-hosting is that nothing is sent to third parties. This can be very important in acronym compliance like HIPAA or GDPR. This can make self-hosting more than worth the costs in many cases, such as using AI models to analyze trends in medical records, which seems to be a pattern that people are doing for some reason. Nobody is going to even imagine allowing you to pipe all that data to OpenAI or DeepSeek, no matter what acronyms they're compliant with. Also, what if your app touches LGBTQ issues, menstruation schedules, or something that the current political zeitgeist might label wrongthink? OpenAI or the other providers could just turn off answering questions like, I don't feel like my body is right. Is there something I can do to find out why or fix this? You'd just be out of luck. Your self-hosted models, though, would be totally unaffected. Of course, this isn't free puppies and rainbows. There's some significant downsides in self-hosting your AI workloads, and they can be subtle and kind of insidious. The big one is that the NVIDIA drivers are stable, asterisk. The NVIDIA drivers will become the bane of your existence. They're normally stable, but they can and will fall over at notice at 3 a.m. That is the SRE witching hour. It'll never fall over during work hours, because why would it? It's always during the witching hour. You'll have to deal with the NVIDIA drivers that have no introspection into what's going on, suddenly deciding that, you know what, uptime, that's for cowards. You can work around this with worker pools and redundancy. That can change the price considerations. Everything's a trade-off. Another downside is that you have to choose what models you're using. There's so many options out there, it can be paralyzing. Like on Hugging Face, there's probably over 1,000 different variants of Llama 2, and God knows how many models total. But like I said earlier, the Facebook Llama models are a good place to start. They're generalists, they're good at a lot of things, not really good at anything in particular. It'll get you a feel for what's possible. Eventually, you end up learning how to pick models for individual things. This is a skill you have to learn. It is learnable, but you have to learn it. Again, everything is a trade-off. Also, when you're self-hosting, you have to have opinions about how things are done. You have to choose between OLlama or Llama CPP or VLLM, or know how to use the Python stack to do whatever you want. This is fine. Like, I use OLlama for a lot of my stuff because it works well enough that I don't have to think about it, but you have to have the opinions. I had to spend the time developing the opinions. It'll work out. It's just, you have to have the opinions. But the time to have opinions doesn't really exist when the boss is breathing down your neck, wanting to show investors the sparkle emoji button. There's only one problem with self-hosting that's not as easy to work around as just having the time to have opinions. When you do this, you're going to need GPUs by NVIDIA. Like, sure, you can try other things like AMD GPUs or try running it on Apple Silicon. I can't stop you from hurting yourself. Realistically, NVIDIA cards are the path to least resistance in production. The lead time for NVIDIA GPUs is measured in months. And you can only get like single-digit numbers of them. When you do get them, they're really expensive. We're talking on the order of $40,000 per card. And you can only buy them in packs of 8 with like high-end all-yes config servers. Like, one of those servers costs like $200,000. Not to mention the fact that they need like 5 kilowatts of power at full bore. And not to mention the data center technician time to handle the hardware failure. Like, sure, you can get the cards you need off of eBay, Taobao, Alibaba, or GPU Craig on Craigslist. But sooner or later, your employees are going to run out of spare kidneys. You'll run out of budget party for all the pizza parties to make up for the kidney donations. And venture capitals want a return on investment. Even more fun, when you do get those GPUs and you have them full bore, service life of 1 to 3 years. Then you get to start it all over again. I'm kind of amazed that anyone's able to really put up with this, but this is the kind of hidden cost of AI that they don't tell you about in the sticker price. I don't know if it's really worth it to self-host everything. I did the self-hosting flow for my chatbot, for my home lab, and it did work, but there's just one problem. NVIDIA seems dead set on making sure that consumers have like the bare minimum amount of VRAM they need to render polygons and nothing else. I wanted to experiment with bigger and bigger models, but I didn't have enough dedicated VRAM. I had to branch out into the cloud. So there's got to be some middle path between these two extremes, right? Both of these just seem like they're different types of suckitude. There is a middle path. It's called nomadic compute. This is a buzzword that I'm trying to introduce into the collective unconscious of the technology industry. Nomadic compute is cheating, but strategically cheating, and knowing exactly how and when you should cheat. It all revolves around taking advantage of user patterns and the fundamental constants of the infrastructure we're all working on top of. In a nomadic compute setup, imagine your workload hunting down the best deal between providers based on the exact requirements of that workload. You spin up more when you need them, you slay them off when you slay the excess off when you don't. It's a pretty good thing in practice, I've found. The biggest key to how this works is by taking advantage of one fundamental constant between every provider. GPUs are fungible. There's nothing really special about any one A100 compared to any other A100. The main difference is the price and the amount of video memory. Also, every cloud provider and their mom has GPUs these days. I've seen single-person VPS companies on lowendbox.com advertise NVIDIA GPUs. They're everywhere. And because there's so much competition, you can get a good deal from basically anyone. And also, from an AI standpoint, there's only 3 specifications on a GPU that actually matter: the model year, the amount of video memory, and the memory bandwidth. Every other spec on the GPU doesn't matter, because fundamentally, language models are constrained by the amount of VRAM and memory bandwidth. And the model year is a proxy for how fast the individual processors are, but that doesn't matter as much as memory bandwidth. More model year number, more faster. More VRAM amount, more bigger. More memory bandwidth, more throughput. Like, that's it. And also, you don't need the newest possible cards. My AI workflows actually use older cards that are now 3 generations old, like the NVIDIA A100. It is way more than sufficient for my needs, but because it keeps getting 1 generation older and older, the price per hour goes down. I pay less for the same experience. But if you try to make something yourself to switch between providers, you're going to look like this. All of the APIs have different corner cases. There's lots of undocumented fundamentals about every cloud provider, because why would they document how the entry point in your Docker image starts? Like, why would you need that documented? You can just figure it out, right? Luckily, though, it's the future. And there's this tool, SCaLE. The TLDR of SCaLE is you describe what you want, and then SCaLE, loaded up with API keys for a bunch of different platforms, SCaLE will figure out the best deal for you and just start it up there. You could even have it auto-scale workloads based on HTTP request pressure. So you can just sit back and let your app go viral because the infrastructure layer will just figure it out for you. So when you're trying to implement a nomadic compute setup, I wish that I could give you like a push button receive bacon example, but this is diverse enough because as much as I'd love to say that it isn't, AI stuff is all really specific to the exact use case. Like, you know, like generate text, or given this image, is it a picture of a horse? If you're trying to do this for yourself, keep these ideas in mind. Make everything as boring as you possibly can. Sure, you may want to use DynamoDB or something else that only one provider provides. No, do not do that. You have already spent all of your innovation budget on the AI. Pick super boring and battle-tested tools. Use Postgres. Use object storage. Don't use anything local, and make sure that whatever you do, you can run it anywhere with an internet connection and an NVIDIA GPU. By the way, fun fact, WireGuard lets you run it in user space. Take advantage of this. In your 3-tier web app diagrams, like I said, put your AI infrastructure in the same tier as databases. Like, really, in the 3-tier architecture, you have the front end, the back end, and the weird ancillary support services. These just so happen to usually include databases or whatever microservices you have in your cluster of fun, right? And what is a database server but just an internal service with a weird API? Your AI services are the same. Finally, scale things down when they're not in use. Why should you have to pay for compute time that's sitting there doing nothing? Cold starts can suck, but nomadic compute is cheating. One of the big ways you can cheat is by putting your model weights directly into the Docker image. This does have scaling limits, like Docker will not be happy with a 140 gigabyte floating point weight file, but there are ways that you can work around and mitigate a lot of the suckitude. Also, with many platforms, while the image is being pulled, and if the image contains the weights, you don't pay for the pull time. Think about that. Auto-scaling is love. Auto-scaling is life. So an example of nomadic compute is one of the chatbots that I've made over the years called Mimi. Mimi is one of the characters in the zyaso.net cinematic universe, and when I made her into a chatbot, I wanted to make something to amuse people and make them laugh. But like any good project, Mimi is actually kind of complicated and has a few microservices, because why not? Mimi gets chat messages from Discord. If she's interested in them, I have like this complicated, do I need to pay attention logic. It passes them to the GPU over a service a friend made called Glaceon. Glaceon connects over to the cloud using user space WireGuard to get to the copy of Ollama, spin it up when it needs to, spin it down when it doesn't need it, and then the Go code decides what to do next. If it decides that it wants to draw an image, it sends a request to this ancillary support service called Faline, which sends it to fal.ai, and then Faline gets the image back, it puts a copy in Tigris, sends the URL back to the bot, which uploads it to Discord, and people see a picture of a cat dancing tango. I don't know why they'd want to, but that's the power of AI. Mimi remembers things long-term with PG vector. Okay, Mimi should remember things long-term with PG vector. She's just very bad at it. I need to fix it. This is my second conference talk this week. Maybe I'll fix it. Maybe I'll have time. Who knows? But like I said, when I started out, I wanted to self-host all the things so I could have Mimi be one of the only AI chatbots within my group of friends that actually did that. I wanted to run everything on computers that I could look at, which, by the way, it's a very great way to describe self-hosting in like computers that you can look at. Reality got in the way. Mimi used to run across 3 nodes in my home lab. One of them ran Ollama, and that's what generated Mimi's responses. Sometimes it sent a tool call request, and then it would send the request to Comfy UI, and that would upload the image to the cloud, spit back the URL, and then Mimi would use that to post it to Discord. This worked really well, but then a shiny new toy came out. Facebook released Llama 3. It had 70 billion parameters. The benchmark said it was good. My MacBook had enough RAM to run it, and I did some testing with a version of Mimi, and it worked really well. But there was a small problem. It needed 48 gigabytes of VRAM to run. My home lab server has a GPU with 12 gigabytes of VRAM. As we all know, 48 is like 4 times bigger than 12, so that won't fit. This is when I had to compromise, and this compromise led to me envisioning the idea of nomadic compute. It's okay to use the cloud. Just make sure you have an exit strategy. So when I've been using the models, I've been making sure to use open weights models so that I can put them somewhere else if I need to. I reach out to the open weights models over a private network. I have like dynamic auto-scaling logic and all that. And this allows me to move it around should I need to. Like, sure, it would be inconvenient, but it would be a mild annoyance, not a showstopper. I use the same API, I just hit a different endpoint. Remember, GPUs are fungible. If you can get the thing to do the same thing somewhere else, and it's cheaper, why not? It's okay to ship parts of your AI apps out to the cloud. You just have to make sure there's an exit strategy. Like, here's a great example of how you can make those sets of compromises. When I have that image drawing tool for my AI bot, originally I was using Stable Diffusion 1.5. That model is one of the older ones. I find it can make some really good aesthetically pleasing results, but I have a lot of experience with it. It runs on basically no VRAM, but there was one big problem that I came into. Mimi's model did not generate things that were optimized for Stable Diffusion 1.5. The results could get biblically accurate. To save your sanity, I'm not going to expose you to how bad it could have gotten, but trust me, when you're trying to get a picture of a cat doing tango, you don't want that cat to have 5 heads. Flux came out, and in my testing, the prompts that Mimi generated actually resulted in reasonable things with Flux. Flux was too big for my home lab again. 12 billion parameters, but in practice, it needed like 20 gigabytes of VRAM. I would have to get an RTX 4090, and in Maple dollars, that's like many dollars. I didn't have the power budget for that. I could fit it onto my gaming GPU if I squished things in, but then I couldn't use it for gaming. And then I found out about FAL. FAL could just run Flux for me, and I pay for the output per image. With the exact model that Mimi uses, I pay 3/10 of a penny per image. That is literally less than the power I'd pay to run the power cost for running the model locally on a 4090. It just made sense. But remember, worst case, it's using Flux Schnell. So I can just take Flux Schnell and put it somewhere else if I need to. All with the power of nomadic compute. And as a result, this is what Mimi's infrastructure looks like. Everything that can turn off when it's idle does. I get Mimi to scale down when she's not in use, but Mimi has to stay connected to Discord. It's pretty nice in practice. I've done the math, and I pay about $5 per month for the cloud stuff that Mimi does, and most of it is inference time for the GPU. For what's going on under the hood, I think that's really cool. Before we finish this up, I'm going to cover some of the biggest lessons I've learned running AI workloads that'll save you time and money as you implement the sparkle emoji for your boss. Every input to the AI model matters, and like even small changes to things can drastically alter the outputs and behavior of your product. Like there was this paper that Apple wrote where they had they were trying to get the model to see if models had an internal worldview. So they asked the question, what weighs more? 2 pounds of bricks, 1 pound of feathers, or 3 pounds of air? AI models almost always said the bricks were heavier. Generally, when you think about AI systems, you kind of want to think about it like this. You take the prompt, you pass it through the XKCD comic of linear algebra, and you get the result. And you just mangle the langle the right way, and you get an output. And usually this is the case, and usually it works out. Asterisk. Sometimes there's hidden inputs in the mix that can seem pretty banal, such as the date and time of the user making the requests. This can have hilarious results, like Claude gets lazy around August. August is stereotypically when Europe goes on vacation. ChatGPT gets really bad output in December, around the time when Americans ritualistically give up for the year. If your app doesn't need a bit of input, don't give it. This will make your models way more deterministic. Also, most platforms and inference engines will let you set the seed value that the model uses for its randomly selecting tokens, for seeding the diffusion space or something. Pick a set seed for everyone, such as 3,407, which I have found an academic paper that clearly demonstrates that 3,407 is the best seed, and they don't know why, but they have found that it's the best seed. This will make your model way more deterministic, because if you change the random seed, you make the randomness deterministic, eh? Also, one of the other main parameters you have for AI stuff is something called the temperature. The temperature is what controls the randomness of the output. Higher temperatures can cause more amusing results, but higher temperatures can also cause the model to become wildly predictable and go off the rails. Set the temperature as low as possible. To make it easy, I have a table. And this table is for the task and the desired temperature. If you need things to be strictly factual or for data entry or summarization or something where the details matter, the temperature should be 0. There should be no additional randomness. It should be as deterministic as possible. Otherwise, you just have to use a technique that the AI industry, unironically, real life, calls vibe eval, to just figure out what number works best by the vibes of the response. My chatbot Mimi uses a temperature of 1 because, let's face it, the worst case scenario for Mimi is that people are going to laugh. Nobody's going to be negatively affected if she just says, tacos are made out of, taco shells are made out of cheese. I'm also pointing this out because some inference engines will set the temperature to 1 by default if you don't set 1. And this can and will bite you. I had to find that out the hard way. Another strategy that you can use is something called filter models. Because let's face it, users will try to break your model and make it tell you how to make pipe bombs. You don't want your AI product telling people how to make pipe bombs, because that could get you love letters from the FBI. You don't want love letters from the FBI. Thankfully, Facebook, Google, and other companies have created this paradigm called filter models. A filter model is something that sits in the middle of your AI flow. If a user input passes the filter, it goes to the model. If it fails, the user gets info that it failed, and if you're polite, you'll tell the user why it failed. The output of the model is also passed through the filter to make sure the user didn't manage to smuggle an input that makes the model generate an unsafe reply. This can help you make sure that user inputs are passing muster or standards or something, and making sure that your AI models don't advocate for obviously horrible things under your nose. The two most popular filter models are LlamaGuard from Facebook and ShieldGemma from Google. ShieldGemma? I think it's ShieldGemma. Both of them come in a few different sizes, but something of note, that says LlamaGuard 3 8B. That is 8 billion parameters. Most of the models that you're going to use for production stuff, you should probably start at 70 billion parameters, but LlamaGuard 3 is the thing that I'm recommending, and it's only 8 billion parameters. You might wonder, why is that? That's because a specialized fine-tuned model can always be smaller than a general purpose model. If you're fine-tuning it for a specific task, such as making sure the user isn't asking how to make a pipe bomb, that doesn't require as much general intelligence as, how do I make apple pie, or given all of this data, which company is performing the best? Or, I forgot, Alexa, how do I make pancakes? Fine-tuned ones are fine-tuned specifically for the exact use case you need, and they can always be smaller than general purpose models. When I've been running Mimi in my home lab, the part that I left out is the cloud model runs in the cloud, but the filter model runs on a local GPU in one of the machines I can look at. You could also get access to hosted copies of these models. I think Facebook's offering an inference thing, but there's this website called OpenRouter where you can get access to basically any model under the planet, or on top of the planet. Also, filter models have been very bad in the past, but they've gotten way better. One of the funniest ways that LlamaGuard backfired me in testing was that one day that Mimi decided that everything was election interference. Language models have gotten better, which have made this better. I'd love to see what a reasoning filter model would look like in practice. That sounds like a bunch of chaotic fun. In conclusion, AI stuff isn't scary or expensive. The devil is in the details of how you balance the complexity around, but you can cheat. Tools like SkyPilot and philosophies like nomadic compute can help you make sure that the workloads are sustainable. Your model can't be deprecated if you host it yourself. Host what you're most comfortable with. Buy the things that you're less comfortable with. This will mean that you're going to spread your workloads between clouds, but you'll be less beholden to any individual platform. And if they jack the prices up, you can actually just leave. Other platforms will be there with open arms and good deals. Cheat. Take advantage of user behavior. Batch processing is back. You don't need to pay for idle workloads, so spin them down. Users don't need the sparkle emoji button to work if they're asleep. Also, if you can't self-host a model, make sure there's an exit strategy by having the model be self-hostable at all. This means that if a provider goes insolvent or deprecates the one AI model that you're using, you don't have to worry because you can get it elsewhere. It's if you're familiar with the concept of hexagonal architecture, this is kind of similar if you look at it from a moving plane, but it works out in practice. Before we get things wrapped up, I want to give a moment to give special thanks to everyone on this list for helping make this talk shine. Thank you so much. And thank you for watching. I've been Z Yasso, and I'm going to linger around for questions, but we have time for questions right now. But worth noting, if I don't get to you and you really want an answer, email mimibestbot@zserve.us, and I'll get back to you as soon as I can. Like I said, this is my second conference talk this week. I fly out home to Ottawa tomorrow morning. I may take a while to respond over email because I'm going to pass out and sleep for like 3 days. I have a link here to supplemental material on the Tigris blog, and there's also some things that didn't make the cut for time. Scan it with your phone's QR reader. I promise it's not a Rickroll this time. Either way, have a great conference all. I've got stickers. And we have time for questions.
Yeah, we'll open the floor to questions.
Yeah.
Yeah, so I'm in the self-hosting phase right now. So what if, as the models get better and smaller model could make do, or I'm just using a very specific model, would self-hosting still work? Do I really have to go that way with the cloud?
You can't, okay, so there is something that has been happening. Like when Llama 3 first got released, Facebook released the 405 billion parameter model. It was the biggest open weights model that scored the best. It was like scoring the same level of GPT-4. At the end of last year, Facebook released a 70 billion parameter model, Llama 3.3, that scored just as well as their 405 billion parameter model did. And in general, there seems to be some sort of like scaling wall at GPT-4, and because a GPU VRAM is so limited, every company is trying to find ways to make models run better on lesser hardware, because if you can unlock being able to use consumer GPUs, you know, like you don't have to pay for you don't have to have employees donate their kidneys to get more servers. So we're going to see more local stuff.
Yeah, to that end, I was wondering if you've looked at two like techniques. One is quantization. Maybe you've had some hilarious results by doing that, but that seems like a low-hanging fruit to try. And then the other one was decomposing a model so you could run it on like multiple nodes. I'm wondering if anyone's working on that.
Quantization, I forgot to mention quantization in this, but yes, effectively models are giant bags of floating point numbers. Quantization is the process of doing lossy compression on those to make the bit size of those floating point numbers smaller. Personally, when I do most of my AI workloads, I run my models at 4-bit integer quantization, and like the difference between there is some loss from the like 16-bit floating point to the 4-bit integer, but I don't know what it is, and the vibes are fine, so like it's good. There are methods of distributing models between machines. I tend to like single GPU setups because they're easier to think about and they're easier to spin up and down in groups. I do know that Apple Intelligence, with their server model, they do have a ring of 3 M2 Ultras for doing their big model. Does anyone else have any questions? There's a microphone.
Could you just follow up as well on the horizontally scaling models as well? Which was, I think, your question? Like if we're doing that right now, or what that could possibly look like for smaller
Horizontal
CPU?
scaling, the main barrier there is GPU silicon. And otherwise, it's just normal auto scaling. Like, you could probably, if you have the right setup, you could probably do it with a horizontal pod autoscaler in like AWS with Amazon's managed Kubernetes. I mostly do my horizontal auto scaling by having something manually contact the vast.ai API and spinning things up and down on demand. But like, everything's a trade-off. It's just a simple matter of programming, you know? There's another one.
It was a really good talk. You mentioned something in your presentation about hosting the weights on the server and then using an API call to access those weights. I wonder if you can say more about that. I thought that was pretty interesting.
Let me find that in the slide real quick. Mostly so that I have like a visual aid for this. But okay, so like I said, models are giant bags of floating point numbers. And generally with your inference setups, you're going to have like a bunch of models that you could possibly pick between and the models that are actually being used. So what your model storage thing, like in Tigris object storage or like NFS, if you're feeling old school, is going to basically just be like a big thing with a bunch of hard drives. Like here I have the oxygen icon for like many hard drives piled on top of each other just to symbolize, you know, like storage, big data, bigger than RAM. And the model storage stuff is kind of important because it's a place where if that fails, that can have lots of side effects on the rest of your setup. Like in my home lab, I have the stuff backed by Tigris in the cloud, and then I have it locally cached into Longhorn and also replicated across multiple nodes in the cluster, so that like if my GPU node does die, that the Longhorn will just be like, oh, the GPU node died. I'm going to go rebuild the disk image now. Like the Olama pod won't be schedulable because I hard code it to that exact GPU model, and that's the only machine in the cluster that has it. But like the data will not be lost.
Okay.
But the stuff local to the home lab is mostly a cache.
Okay, gotcha.
There's one in the back.
Hi. So for the temperatures, you had summarization and like for analyzing financial documents.
Yeah.
I was wondering what you thought of for classification. Would that be like closer to summarization, or what your thoughts are on that were?
I would need to know more about the task at hand to give a good answer for what temperature to use for classification, but generally start with as low as possible. Start with 0 and work your way up to find what works best. And for some reason, the seed 3407 is all you need. I don't know why either, but that seems to work.
All right, thank you.
I have the slide at the end with the QR code has a link to like all of the stuff, including that paper called torch.manual seed 3407 is all you need. Any more questions? Oh, perfect. It's at tigrisdata.com/blog/affording AI chatbot friends. Oh, great. I thought I fixed the QR code. I think I loaded the wrong slide deck. I am sorry. I will get an amended version of this as soon as possible. Actually, hold on. Let me find my phone and hit merge on a PR on GitHub, and it'll show up on the blog for Tigris. I would do it on the screen, but I don't feel like leaking GitHub secrets to you today. I'm sorry. We could have had exciting, we could have had NDA violations, but you know, we're not doing it this time. I mean, yeah, you're getting live updates during the talk, yeah. Okay, so merge pull request. Make a thing public. Okay, it will be on the main blog page in about a minute once SCaLE builds it. So we have a workaround. You had a question?
Well, I had both a comment and a question. On the CFAR data set, that value 3704, 3407, I'm imagining that the reason that number happens to work better is just because something like 2% of the images are mislabeled in that data set, and it's probably just getting accurate answers, you know, sort of randomly. Good point. I was wondering about that.
I don't entirely know why it works, and like if you read the paper, this guy will say like, I have done some intensive looking into this, and I don't understand why it works, but it makes the number go up, and like you want the number to go up, right?
So, yeah, it's a fluke though. You know, sometimes
Yeah.
you win a jackpot. I had a question. You made a comment, and I was typing at the time. Something about using WireGuard, you could run something in user space.
Yeah.
And I didn't quite follow that. I was wondering if you could
Okay,
go over
so WireGuard is a VPN protocol, and it takes stuff, it takes like IP packets, encrypts them, and then fires them out over UDP to a target. There is fundamentally nothing special about this that prevents you from running it in user space. Like there's the WireGuard Go library published by the WireGuard team that can let you do this. It uses a library called NetStack made by the Google gvisor team that has a full TCP IP stack in user space because, like, let's face it, TCP IP is just weird but bitwise math, right? So yeah, it's possible to run it in user space, and in my experience, I found that user space WireGuard allows you to have your services join your network, kind of like Kubernetes, but kind of like halfway between Kubernetes and not Kubernetes. Yeah, like I was working on a.
It's easier to set up the whole stack of things you're saying.
I was working on a capture the flag thing built on top of user space IPv6 like that. I need to finish it at some point. That could be a fun thing to release on April Fools. Any more questions? No? I think we're good. Thank you. Like I said, email mimibestbot@zserve.us, go to tigrisdata.com/blog, and you'll get the link to the resources. I am so sorry the QR code did not work. I thought I tested it, but who knows? Maybe my laptop synced the wrong version. Thank you so much.
Our next talk will be around 6:15.
Testing, 1, 2, 3. Testing, testing. 1, 2, 3. Testing, testing. Kind of, maybe. All right.
It's green, it's on, and all the good stuff. I'll start you off again like around 6:15. I hope it's okay.
Yep, perfect. Yep. It's always, the low stress option's always good. Cool. All right. Appreciate it. Von Thenen. Yeah, there you go. Yep. Yeah. It's all good. It's difficult. Yeah. Let's see. While we're waiting here, I have some t-shirts left. 2XLs. Oh! 2XLs, and I have an XL too. XL? 2XL? XL? 2XL, 2XL, 2XL. 3 more. 2XL. T-shirts, courtesy of DigitalOcean. That's a 2XL. Oh, sorry, that was horrible. I was going. Yeah, no, these are literally the last one here. 2XL. 2XL? Oh no! Oh, there we go. Awesome. I'll have some stickers too at the end, but all the t-shirts are gone. Excellent. No, I got water. Yeah, I think I'm good. Wow, this is actually more people than I expected. So I'm just curious. So me and my other co-presenter here, we had a session yesterday talking about building machine learning models to detect Parkinson's disease. Anyone who showed up for that at all? Okay, I was just checking. Yeah, because actually one of the things that we're going to talk about in here, we directly applied to that, so. No, it's okay. Chat amongst yourselves. Yeah, I know. What? Yeah, there you go. And I know we have game night kind of the last 15 minutes, so hopefully we'll definitely finish before then, so. Who's going to game night? Yeah, it's a lot of fun. Board games and yeah. Do you know if they have alcohol this year? I know last year they did not. Okay. Right? Yeah. What? Yeah. Oh, we got some people coming in. I know. It's like, I guess, kind of while we're waiting. So yeah, this is hopefully, I kind of like to think of this as like the 101 to building natural language models. So we're gonna like literally build them and like talk about how to build them. And I think it's really cool because it's kind of like a fundamental, like if you kind of understand how this works, then you can start to apply like some of these concepts to like fine tuning and like how does AI, like, you know, LLMs work and stuff. So I think it's pretty cool. So. Come on in, everyone. This is yeah, for sure. It's all good.
Evening, everybody. Introducing our final speaker for today, at least in Ballroom F, David Von Thenen.
Yes.
After his presentation, we'll field some questions for him. So hand it off to David.
Cool. Thank you. Thank you. Yeah, so we're going to talk about how to build NLP models, so natural language processing models. We're actually going to start very simple, and then we're going to go to a far more complex model. And kind of the whole idea is like, just like the title says, it's like demystifying it. Everyone thinks like machine learning and AI is like super difficult. And like I'm trying to, this is hopefully to break down some of these barriers, and it's far simpler than it actually sounds. So hopefully we'll do it by example. And I'll have some cool resources for everyone here at the end so that they can try it out on their own. So my name is David Von Thenen. I am a AI ML engineer at DigitalOcean. I've been in the AI ML space for some time here. I particularly came from an NLP background, although I love doing vision-related stuff, you know, RAG, building IoT edge models, you know, doing AI and ML on edge, even like training medical models to detect disease. Prior to that, I was in the Kubernetes and CNCF ecosystems, so working on open source Kubernetes. And then prior to that, I was doing backup recovery solutions for virtualized environments, specifically VMware vSphere. So the agenda today, we're gonna do kind of like the hello world. So this is a very basic, we're gonna build a model right here. And it's gonna be a very basic model that is a classifier to identify whether a sentence is a question or not. I kind of think of this as a very simple hello world. And then we'll move into something far more difficult, but you know, easily digestible here. So we'll do a named entity recognition model. I think in the talk on what it was actually going to be, we'll talk about it at the end. But for doing redaction, you have to do named entity recognition first before you do the redaction. And then we'll do a demo. I'll do it live. We'll have several demos actually, and I think 3. And we'll have a bunch of resources for you to try this at home, and then have a bunch of Q&A. So our very first NLP model, and I'm gonna kind of start level set with some terms, just to kind of break this down, make sure that we can all understand all the terminology and all the jargon. So whenever you build like a machine learning model, it always starts with a data set. So what's the domain that you're trying to do, whether it's natural language processing, whether it's doing images and vision related classification, whether it's doing medical analysis with MRI images, you have to start with your data set first. This is like what you're trying to identify, classify, you know, that whole bit. And you know, with that data set, the whole idea when you're doing classification is that you're trying to find patterns that exist in this particular case in language, right, in natural language processing. So once you have your data set, you need something to like decompose language, right, so sentences. And you do that by a tokenizer. And everyone kind of has heard, you know, like large language models are kind of just next token prediction engines. And they are. In fact, you break down language to very concrete, small blocks, and you just basically predict the next block, and then the next block, and the next block. And so there are a lot of ways of doing that, and there's a couple of them here, and we're going to use the first one, which is BERT Uncased. So BERT is a natural language model that came out of Google, and it's case insensitive, and it's basically trained on the English language. There's a whole bunch of other ones that are, you know, language agnostic, where it works on multiple. But this is a great simple one where you can start with to tokenize or break down your sentences into single words. And then there's another one that's DeBerta, which is kind of like a slightly more advanced one that came out of Microsoft. What's really interesting and cool about that one, the tokens, or the smallest unit of measure for DeBerta, doesn't have to be words. It can actually be like syllables, which is kind of very interesting, like broken down words. And it's kind of really fascinating. So you have a data set, you have something to break down to get to an individual token, then you have a machine learning framework, and this is something like PyTorch, TensorFlow, and then I have Fast AI here, which is kind of very interesting. It's kind of meant as like a beginner's or starter's guide to like hiding a lot of the complexities away from PyTorch and TensorFlow. And it's kind of an easy way to get started with doing machine learning. And then I even started with that a long while ago. And once I kind of got like the knack of it and like understanding how to build a classifier, I, you know, evolved away from that, and now I use PyTorch, and we're going to use PyTorch here today. I have some other terms that are, you know, you hear. Like a tensor is just a measurement. It could be multidimensional, but it's just a measurement. So whenever you hear the word tensor, think I'm measuring something. And then some other popular frameworks are Pandas and NumPy, or NumPy, however you want to pronounce it. They're just other ones you should take a look at. It helps you manipulate data in large tables and contexts, right? So for your first NLP model, so the classification, NLP models specifically, classifiers are they're like the basic foundation. When you build a classifier, in this particular case, if we're building a classifier to determine whether or not a sentence is a question or a normal like statement, it's literally two types of classification. Is this a question? Is this not a question? And so when we're building a machine learning model, you need to start with a data set. And this sometimes can be very difficult depending on the problem that you're working on. And so curating that data set and finding that data set is sometimes very difficult. In this particular case, there's actually a data set that already exists that provides, it's called the Stanford Questions and Answering Data Set, or SQUAD for short. And so you actually, if you go to the Stanford, I think it goes, well, it was a data set that was curated from Stanford University, and it literally has questions and then the associated answer to that question. So if you're trying to build a question and a sentence classifier, this is actually a great resource, a great place to start. So if we have this data set and we are trying to classify whether a sentence is a question or not, we can literally break it down and put them into two categories. Grab all the questions, and I can actually show you when you get to the demo. Grab all the questions, or grab all of the sentences, whether it's a question and answer, and put them in one column. And then the second column, if it's a question, you literally have a 1, and if it's a sentence, you literally have a 0. And so if you're trying to build a question classifier, when you present a question, once you train your machine learning model, and you present a question to your classifier, it's literally 1 or 0. Is this a question or is this not? And so when you build a machine learning model to do a question classifier, it is literally that simple. You have the tokenizer that will take all of the sentences that you've provided, sentences, questions, and everything. It'll break down the sentences into words, and it will find the patterns that exist in those sentences. When it finds those patterns, it will see that there's a 1 or a 0. Is this a question or is this not? And it's the simplest, NLP classifier that exists because it's super simple. Column, sentences, 1 or 0. Is this a question or not? So it turns out this problem is actually far more complex than it sounds. That is actually how you build the classifier. But what's kind of very interesting about this is, if you're trying to build a question classifier, couldn't you just look at the end of the sentence and look for a question mark, right? And it turns out that if all of your sentences have question marks at the end, your machine learning model will literally learn that if there's a question mark at the end, this is a question. And so there's actually some things that you need to do in order to make it so that it doesn't do that. We have some sentences here, and what's kind of very interesting is some of them are very simple, like, is this an example sentence? Question. So this is obviously a question. My name is John Doe, period. Obviously not a question. How are you doing, my friend? So there's no question mark on the end of that, but we know that it's a question, right? Because we just know that, right? It starts with how, usually who, what, when, where, or how, is usually another identifier. So when it breaks down, so when you're building your machine learning model, it's going to tokenize and pull out the words that are contained in the sentence, and it's going to learn and it's going to identify that how is going to be an identifier to classify this as a question, independent of having the question mark at the end of the sentence. Now the last one is very interesting. Tell me about the history of the United States. That is a question. It doesn't end in a question mark, and it doesn't even begin with who, what, when, why, or how. But when you ask someone this, you're eliciting a response from that person, and so we want to have this come back as a question. And that's why this problem's slightly more difficult than it sounds, because we want to have that last one come back as a question. And in fact, when we're going to build this machine learning model out, it will actually do that, which is kind of cool. So let's just go ahead and take a look. So it's already pre-built because it actually takes some time to build this, but that Stanford question and answer data set that I had talked about, I'm going to open up the dev version of it so it's much smaller. So you can actually see it's in JSON. You can see the question here, and then you can see the possible answers. And what you can do when you build this out, you put the question and the answers in one column, again, and then 1 or 0. Is this a question or is this not? No, it's not. We're going to extract it out of the JSON and then put them into a CSV or just a CSV file. So if we actually want to take a look at that. So when you do the extraction on that, and there's this main.py which actually does that. If I deleted all of the CSV files here, it will actually download the Stanford in question data set. It will extract that out. It will create a questions data set. Oops. Right? Questions. What do atoms form? Comma 1, which means it's a question. And so it'll grab all of the questions, extract it out from that JSON, put them in there. I've separated them out so you can actually do cat. Where is the non-questions? So these are like non-question, right? It's just text, right? It's a standard sentence, comma 0, not a question. And then they end up getting combined into this data set here basically merge the two CSV files into one CSV file. In the main, it will train the machine learning model based on that CSV file. And believe it or not, it will come out, you'll have a model that pops out the other end, and then when you actually run it, is this an example sentence? Is a question. My name is John Doe, not a question. Tell me about the history of the United States, question. And so, believe it or not, it sounds like I'm like glossing over a bunch of stuff. The point is, it's literally that easy. Like 2 columns, sentences and questions, ones and zeros, train the machine learning model. Its job, like PyTorch's job when it's deconstructing and decoding everything, its job is to handle all of that stuff for you. Train the model, it outputs this model right here, and then you can inference it by giving it test questions, which are these ones right here, and it will tell you whether or not it's a question or not. So it sounds incredibly simple, but literally, that's kind of like the point of this hello world. It's literally that simple to get started. Sorry, what? So no, it doesn't have to be. So we'll actually get into the next one, which is the more complex one. So cool. Here's just a summary for your own information, just a recap of everything. In the data set, so like all of the questions had question marks at the end, all the sentences had periods at the end. For 30% of the data contained in both of those categories, I removed the punctuation. And the reason why I did that was because when I type, especially like on Slack or something, I don't punctuate half the time anyways, commas or anything like that, right? So removing that basically then forces your machine learning model to learn that it's not all about the question mark. So, super simple example, let's now scale that up. So we're going to build a named entity recognition model here, which is also redaction, but we need to start with the named entity recognition first. So what are named entities? So named entities are extracting and classifying things in sentences mentioned in unstructured text into predefined categories. So if anyone's heard about like personal identifiable information, protected health information, payment card stuff, so like credit card numbers, CVV, those are all different classifiers or classifications for things. So like my name, David, the classification is name, right? If I was like my address, the classification would be an address. So kind of like the point of it is when you're building out one of these classifiers, in this particular case, it's a named entity recognition. Think of it just as taking the text and associating a label to it, so that when you want to classify it, it's going to see what that label is and understand that that word is classified as that particular label. And that is literally how you build out a named entity recognition model. I think we had a question. Like identifying medical words and, yeah, 100%. So what's interesting is you start with sentences, because we're talking about natural language processing. You start with sentences. Whatever you choose to identify or what you're interested in, you would associate a label or something to it. So if you were talking about a movie database, you have a list of movies that you've curated from IMDb. You understand that these are titles. You would attach title to those words, right? That's kind of like the very basic breakdown of it. Right. Yes. Right. I'm going to get into this. I'm going to decompose that. Yeah. Okay, so the most difficult part is where to get the data, right? Again, everything starts with a data set. So for named entity recognition, this is actually a well-known way of classifying data, right? People need to redact or remove personal identifiable information from transcripts. So there are already existing data sets, thankfully. You don't have to make your own. I basically linked to a whole bunch of them here. This first one is amazing. It's literally a GitHub repo with links to other data sets. So if you're looking for Twitter data, if you're looking for movie database stuff, if you're looking for world history stuff, it has like links to all of these other data sets that you can label yourself or just use the existing label that's there. And if you're building a named entity recognition model, there's actually already a format, and it's cool that all of these resources here, all these data sets and these links up here are already labeled in this CONLL formatted data set. And these data sets are, curated and created by, researchers and people who are interested in doing text classification. And thankfully, you can just go ahead and download them, and you can use, if you want to use the predefined labels that they have, you can go ahead and do that, and that's what we did for this particular demonstration. But again, just remember that you're just associating a label to a word or a group of words, which I'm going to cover in a second here. So again, just the CONLL format is a widely, a standard that's widely available. It's a super simplistic view. Again, I keep driving this home, but just like the 1 or 0 is a label for, it's a very simple label for a sentence or a question, you can attach multiple different kinds of labels to words. And so in the case of like personal identifiable information, like if you give your age, you would literally just use an age label. If it's my name, you'd use a name label. And what that looks like in the CONLL format is this. So we have a sentence, United Nations official, I'm going to horribly mess up that person's name, heads for Baghdad, right? You can see the sentence right here on the left-hand column. It turns out with machine learning, you don't need these two middle columns. It's actually, you can strip it out, and in the code that I provide, I actually do that. So the only two pieces that we actually care about is that word column and what that entity tag is. And so if you look here, United Nations is one organization, and you want to treat United Nations as one holistic unit. And so the way you do that when you're kind of tagging or labeling your data is that you have this B or I. So beginning of my organization, and then an I, which means your continuation of that particular entity. So United Nations is the beginning of, United is the beginning of the organization, Nations is happens to be the last one, but it's the continuation of that organization label. And so this person is B because it's the first time. So if I use my name, David Von Thenen, David would be B person, Von Thenen would be I person. And then Baghdad is B location, right? And so, again, it sounds crazy, I know, but you take these labels, you assign them to the individual words, and if you use the data sets that I've mentioned already, they've already done that, right? They already have those sentences that are broken down with the entity tag on the other side. And so if you're just curious or interested about like identifying organizations, people, locations, using the default data sets that are there, you literally just hit train, and when you want to use and classify sentences, it will actually pull out like, this is a person's name, this is a location. And it's like PyTorch and those machine learning frameworks, literally it's its job to identify how these things are organized based on the labels that you're interested in. So if you wanted, for whatever reason, to be notified for heads, like that word, just I don't know why you'd want to, you could literally attach a label that says, B heads, right? And you'd get notified anytime you wanted that particular word or those groups of word classified. So if you were doing IMDb for like movies, you'd have like B movie for like, I don't know, what's a movie these days? Whatever your favorite movie is, if it's more than one word, B would be the first, B movie would be the first word. The next word would be iMovie, 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 iMovie. And then when you train the machine learning model, when you say, I'm interested in movies, it will give you that whole chunk as one huge chunk for that entity. Yes? No, so that BERT tokenizer that I talked about so that's case insensitive, and I did that on purpose so that we don't have to worry about case. Yep. And it turns out if you use public data sets, sometimes the data is labeled horrifically, and it happens all the time. And so even though you have public data sets, definitely take a look to make sure that they're correct. It's just the way it is. And the reason why is that when these data sets get curated, a lot of the times, you know, we pay people to go ahead and label the things that we care about in sentences, if we're talking about NLP, and people make mistakes. And it happens far more often than you think. And why it matters is that if your words are not labeled correctly, with the words that you want to identify are not labeled correctly, it will unteach what you are interested in classifying when you're trying to get entities out. So it's really, really important that when you provide data and you ingest it into your data set, that everything in that data set is as pristine as it possibly can be, because you don't want to kind of like accidentally teach or unlearn like eye location, for example, like to identify locations. And so if we were to build out, and this is where it gets slightly more difficult, and actually I probably should mention, the O entity tag means we don't care about this. We're not interested in this word at all. So it turns out that if we want to build out a named entity recognition, or anything that we want to classify, like a movie recognition system, or actor recognition system, or whatever it is, what the CSV file seriously looks like is, which I'll show you in a bit, is that sentence, and then a new line character to the beginning of another sentence, and then a new line character for the beginning of another sentence, and in the second, or these multiple columns that are there. So if we don't care about that particular word, so like if we take a look at the word is, it has a tag of O, which means I don't care about this. And then all of these other ones are zeros because we don't want it to be classified as the beginning of an organization or the continuation of an organization. And then in the case of the United Nations, it is an organization. We do care about it, so we need to apply a tag so that we can classify that grouping of words as an organization. So United would be the beginning, nations would be the continuation of that organization, and so on and so forth. So if you're interested in like time, like June 3rd, 2012, you can literally, B time would be June, I time 12, 2012, I time. And when you say, give me all of the time entities that exist in this sentence, it will actually do that, providing that you provide enough in your data set for it to teach it, right? And again, we're using BERT uncased, so we don't care about casing at this time. Yeah. So let's go ahead and take a look. Okay. I'll do it, sure. So I just wanted to show you this, I think. Oh. Let's see. So I'm taking this NER directory, which contains my data set. So this is all of the public data sets that I had. I didn't actually do it. I'm going to skip this, sorry. Anyhow, okay, so let's just go ahead and feed it some sentences. So we train the model, so that's what this main.py does. It will take all of the named entities that we have defined here. So these are a whole bunch of different named entity data sets. So you can see, this is one that just came out of, I think it's like the CONLL. They actually have a conference, and every year they come out with a whole new data set for people to use for publicly. Here's a movie database. I think this was in the music database. Just stuff off the internet, SEC filings, which we're going to end up using in the demo at the end. So these are different data sets for different things. And I literally, in that main.py, it's already been pre-labeled. Every word in there has already been pre-labeled with something. Actually, let's just go ahead and take a look at one of them so that you know that I'm not kidding. I'm just going to pick one random one. So this is like what one file, which contains multiple sentences, looks like. So you can see the second incident took place near 00000, which means we don't care about this. We don't ever want to classify these words. And then I'm guessing this is location because it's tagged as B location. And this is also a location, so this happens to be whatever these two words, I'm gonna Kavi Nagar. That's one entity for a location, and we want to group them together, so that's why it's B location and I location. And literally, if you have enough data that is labeled in the way that you want it, you can literally use PyTorch. It will go through, train itself to identify and associate all of the different patterns that are associated with making those labels associated with those words so that you can classify words and sentences. And so what that ends up looking like, so we'll just take a look at this last sentence. So the Eiffel Tower is one of the most famous landmarks in Paris, France. So we passed, after we trained the model, which is contained in NER model, after we trained PyTorch, went through all of that data, it built the model out so that it can do named entity recognition. We took this sentence and we used it as inference. So we basically took this sentence, passed it into the model, and it said, based on all of the labels that we've trained you to identify, return all of the labels in this sentence. And in this particular sentence, it recognized Eiffel Tower as a location. It recognized Paris as a location because there was a comma there. A comma is technically a word, or it's like a token. And so France came up as a second location. And if we take a look at some other ones, just John Doe donated X amount of money, $5,000 to the Red Cross during 2020. So this is a slightly more complex example. John Doe, so given name. So I trained this, I added additional labels in here so that you can do given name, family name, $5,000, right? B money, I money. Red Cross is an organization. B organization, I organization, 2020 is a date. And so if you just use the data set that's all of the data sets that are there with all of the labels that are already there, train it, pass a sentence in, it will do named entity recognition. And it's, again, I know this sounds incredibly simple, which is actually really cool. The whole point of this is like demystify this. This is like, everyone can do this. You don't have to be a data scientist. You don't have to be an ML engineer. You don't have to be an AI engineer. It's literally, it's that simple. So don't be afraid and, build all of the things. So if you're looking to build out a, again, like a movie recognition database, you would have like, if you had sentences or titles for movies, you would literally label it like B movie title, I movie title, actor's name, like actress name, and so on and so forth. I think we had a... So that's what's cool about it is if you give it enough sentences, in the way that the sentence is structured, it will find the pattern to understand that this is a particular location versus maybe Paris the name. That's a great question. And actually the code that I've provided here, main.py, maybe to your point, is there are definitely words that you would want to label as two different labels, right? So maybe, do I have one that's an example of one here? I don't. Because usually when you pass the sentence in, based on the context of the sentence, it will return the label based on like what it is, like a name versus a location.
Can we run this with a sample sentence like, yesterday Paris Hilton visited Paris, France?
So we can. We'll give it a try. So by the way, also too, that this named entity recognition thing, it has definite flaws in it. Like, don't use this for production. This is more an illustration or an example of like how you do it, right? I, believe it or not, spent weeks combing through this data to try to fix as much of it as possible, but it is far from perfect. So just as a heads up for it. But yeah, sure, let's try, why not? So what was the sentence? Oops. Let's see if this blows up in my face. How well? You got that. Oh. It should have returned, in the cases of multiple tags, you would have B location, I location, and I think it's just my output is a little screwy on it, but I didn't go like super in depth into making sure that this is like production worthy, but play around with the code and whatnot, so, okay. Here's just some information for you to kind of like talk about what I had just said. Oh, we're running out of time, aren't we? Shoot. Here's a recap. So if you want to do redaction, you have to be able to identify what it is that you want to redact. So to do a redaction of names, you would first identify a name and then replace it with star, 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 star to redact it, right? So, two cool models that you can build. So let's build a real-world application based on these two models. So let's create a virtual AI assistant. Let's assume, and I know it's a console application, but I'm going to talk into the microphone, and anytime it identifies that it's a question, I'm going to actually have a computer, voice generated, call out to ChatGPT or any other LLM, answer the question for me, and then speak it over the microphone, and hopefully we'll get a response back. And it will also take the sentence and break it down so that it will identify all of the named entities within that sentence. And I've also programmed it so that based on the named entities that we want or we care about, it will give me two cool facts about that particular named entity. And why this is kind of cool and important, if you were to do this and build out a virtual assistant and you are in a sales call, you could do all sorts of cool things like if they mention that they live in a particular area, it will identify that area as a location. It will give you two cool facts about that particular location, and you might be able to use that information to build rapport with your person on the other end. And so a lot of companies do this to do call center assist, sales assist. So they basically mine the conversations that are happening, and when something interesting comes up, it will prompt the user or the salesperson or the call center person with information on how to help that particular user on the other end if it's a call center related thing. Or if it's a sales call, maybe it's, again, something to build rapport, or if the customer mentions that they are interested in this particular feature, it will deconstruct the sentence based on the labels that you're interested in, and it will say, you can program your machine learning model to say, hey, I saw that this customer mentioned this particular thing. We actually have 2 products that do exactly that, and it pops that pop-up in front of your salesperson so that they can actually kind of parrot back saying, oh, you know what, we actually have these 2 things that are available in our catalog of products. So that's why this is kind of useful. So let's go ahead and give this a try. So I'm going to spin up a REST API on top of that question model, REST API on top of that named entity recognition model, and I'm going to talk into the microphone. If it's a question, we're going to have a computer voice speak over the thing and answer the question for me, and every sentence is going to get classified for named entities contained within the sentences. So let's go ahead and give it a try. Hopefully this will not blow up in my face. Here's the service for the question. Here is the service on top of the named entity recognition. And then I'm going to start a small demo application that's simulating a meeting type environment. I live in Long Beach, California. Where is Microsoft's headquarters located?
Microsoft's headquarters is located in Redmond, Washington, USA.
I'm going to stop it there. Okay, so the question classifier identified the first one as a sentence, so that's why we didn't have the computer voice respond and give me an answer. It did detect 2 entities, Long Beach and California. That's actually where I do live. And here's information about Long Beach. Maybe in your sales call, you can say, oh, you know, I've never visited the Queen Mary, and I've heard it's pretty interesting. That I know it was used in World War II or blah, 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 right? And, you know, we all know about California. So here is, so where is Microsoft's headquartered located? It called out to ChatGPT, again, use the LLM of your choice to get this response from the question so that we could speak back to us. It identified Microsoft as an organization. It gave me some facts about Microsoft, Redmond, USA, and that is it. Resources. So I will tweet, if you follow me on social media or whatever, Blue Sky, X, Twitter, LinkedIn. I'll tweet out the slide deck and everything. You can click the link at the top, which will take you to my GitHub repo to build all of this stuff at home. And if you don't have a computer with a GPU on it or whatever, I have a Google Colab notebook for everything that I did here, and also a Kaggle notebook for everything that I did here. So you can build the question classifier, you can build the named entity recognition. That one, if you don't have a GPU, is going to take 12 hours. But you can use Kaggle or Google Colab to attach instance with a GPU on it, and it'll take like 20 minutes or something like that, 20, 30 minutes. If you want to deploy this on your laptop like I did today, I have all of the resources to download this with instructions on how to set up this exact demo on my laptop here, and then some resources for like the speech to text and stuff, and then that last link for the repo, super cool, has all of the different things. But again, kind of the point is, if you are particularly interested, you don't have to use those, the repo with all of the data sets. You can build your own data set based on what you care about, and that's kind of like the point of this talk here. And that's it. Any questions? Yeah.
Oh, so from my understanding, the biggest bottleneck to these machine learning models are high quality data. And I know that a lot of the time that's really hard to get access to a large amount of high quality data. Do you are aware or know or recommend any strategies for if you have a small amount of, high quality data, but you want to expand your, data set without too much effort?
Yeah, 100% you're right. The biggest difficulty is obtaining the data set. Like, believe it or not, if you look at the main PY code that trained the named entity recognition model that you have access to, that's on my GitHub, the code is there, but the most difficult, and it's not even that long, I think it's like 500-600 lines of code to train it all. The most difficult part's the data set for sure, and you have to get creative. Either start academic torrents, Kaggle. Believe it or not, there's a lot of people that are posting really cool data sets for things that might be of interest to you, but 100%, that's the most difficult part. So if you wanted to build a question classifier, another way that I actually had done it was, instead of using the squad data set, I just basically grabbed a whole ton of links from Wikipedia, parsed the HTML, scraped it, and for everything that had a question, I moved it aside to have it be a question. Everything that didn't have an end in a question, I moved that to be an answer or a standard sentence, 1 or 0, lopped off the punctuation at the end, and now you have a data set to classify questions. But yeah, you have to get creative. In talk that I did yesterday with my co-speaker here, we needed to find a way to detect Parkinson's by gait or by someone walking in a video. And believe it or not, we did it, we built it. Me as a person who doesn't work in the medical industry, I'm not a researcher, I'm just a person who loves machine learning and like to do this stuff for fun. Where do you get that data to find like people who are walking across a camera that actually exhibit Parkinson's disease and normal people walking? And so for our data set, we went to YouTube, TikTok, and Instagram, and we downloaded video of people posting stuff about Parkinson's disease, and that's where we obtained the data set for Parkinson's classification. So you have to get a little creative, and just think about different ways of obtaining it if you don't work for whatever these large companies, like Google, Facebook. They're sitting on a ton of like a data mine of information, your information. So that information's easily available for them, but for us, search. There's a lot of researchers that publicly post their data sets, which is really cool. And otherwise, get creative.
So how resource intense is all of this? From, actually the setup that you just ran right now to actually creating your own data?
Yeah, so you mean like to do the training?
Yes.
Yeah, so the training, okay. So the question classifier without a GPU, just using my M3 here, it took roughly about 45 minutes based on that data. And I actually did this because I at first I was like, oh, how long could this possibly take? And the joke's on me for the named entity recognition. I literally had my laptop on for 23 hours and it finally outputted a model. With an H100, the question classifier was like 2 or 3 minutes. And then the named entity recognition model was like 25 minutes instead of literally 24 hours on my laptop here.
Okay, then I had another question. What is it, the API that you use for text?
Wait, sorry. And by the way, I work for DigitalOcean. You can spin up GPU droplets, train your models, and then shut it down, and you're only paying for the time that you're using that GPU droplet. Sorry, I got to do the company plug, sorry.
So can you use the text-to-speech API with, like an open source offline model like Llama or something else?
So if you're looking for other models to do other things, like one really great resource is like Hugging Face. Go to Hugging Face, they have like a whole bunch of open source models to do natural language processing, to do speech to text to speech. That's a great resource for you to take a look at. And then if you find that like in the case of like BERT or DeBerta, which is the Google and Microsoft NLP model to break down language, if you find something that is close to what you're looking for, you can fine tune, which is literally what we did here today. You can literally fine tune those models to make them question classifiers or make them entity recognition models. And so you can start with one of those as a base, fine tune them to turn them into something that whatever it is, problem that you're trying to do. Last question down there at the back. I appreciate you running back and forth.
My job.
So, and I don't know if this is actually a problem with LLMs or like just a theory, but I've heard that supposedly if they get like a really long prompt, it can be a little bit more unpredictable and maybe not have the best output. Is there a similar problem here if it's trying to parse too large of a sentence or a paragraph?
It should be okay, because what I assume is actually happening under the covers, it's taking the sentence, it's understanding the structure of the sentence, and then it's looking at the structure of like the pattern that is closest matching to that label. If it's an O, then we throw it out and we don't care. And if it's like a location, then you get it. So it's basically understanding what it happened before, right? And then when it comes to the token for the location, like a location, for example, it's looking at that and saying, oh, I understand that this is a location, and it's popping it out. So it's literally handling it one token at a time. Cool. Again, definitely I appreciate everyone being here super late. But check out those the Google Collab notebook, the Kaggle one, and believe it or not, I kind of copied word for word what I kind of had just said here into those notebooks, so you can revisit it just like if you were here today. So, cool.
Thank you all, everyone. We will see you tomorrow.
So if you're